An unreleased NASA photo from Mars is circulating online if you're savvy enough to track it down. It captures a subtle blue irregularity exactly at the coordinates in the sky, where the interstellar visitor known as 3 Atlas zipped by during its nearest pass on October 3, 2025. Captured via the Perseverance rover's Mastcam Z and combined by an amateur analyst, the shot gained backing from Harvard's Avi Loeb, an astrophysicist, only to face quick backlash from doubters pointing to image glitches instead of proof. This discovery carries real weight. Telescopes in space monitoring the intruder detected carbon dioxide traces and hues ranging from neutral to slightly green. Blue throws a wrench in that. It hints at possible equipment glitches, Martian air interference, or perhaps material with unusual light-bouncing qualities unrelated to common assumptions. Factor in 7 additional odd stats along its path near the ecliptic, like nickel absent iron, a shape leaning toward the sun, and suddenly this thing challenges easy natural accounts. That unauthorized photo serves as the fissure in the official story, the instant when details slipped past official oversight and sparked an ongoing debate. Stick around to the finish. The true insight from this picture lies deeper than what's visible. It's in the quiet aftermath. Before we unpack the full implications, hit subscribe if these midnight deep dives appeal to you, and drop a comment on your viewing spot this evening. Share your take too. Is this pic legit or evidence of a larger concealment? Let's jump in. First up, the disclosure that rattled enthusiasts. A Mars snapshot got dropped unofficially, and it could upend our understanding of cosmic drifters. On October 3, 2025, the interstellar body labeled 3 Atlas reached its minimal distance from Mars. Roughly 29 million kilometers kept the dusty world apart from an intruder that had no business showing up. This entity had journeyed through the emptiness linking star systems to knock on our solar neighborhood's door with timing that felt almost too perfect. Global space outfits pointed their gear at the encounter slot. NASA, ESA, ground-based, and orbital scopes worldwide. All locked in, all anticipating the insights to decode its true nature. Folks anticipated visuals, spectral breakdowns, validations. Instead, they encountered hush, followed by something way more compelling. A merged photo surfaced on blue sky, uploaded by astrophotographer Simeon Schmaus. It featured overlaid shots from Perseverance's Mastcam Z tool, aligned to uncover dim traces hidden in standalone frames. Right at 3 Atlas's forecasted spot in the heavens, there appeared a blur, subtle, spread out, scarcely noticeable against the dark Martian backdrop, yet clearly blue. Avi Loeb, the Harvard expert renowned for probing tricky queries on space nomads, boosted the photo with a straightforward attribution that lent it official-sounding credibility. NASA/JPL Caltech/ASU/Simeon Schmaus. He called it a dim blotch in the expected spot, obtained by layering several Mastcam Z images. Should it hold up, this would mark the initial instance of a ground-level Mars device spotting an interstellar traveler live amid a near miss. The reveal energized a crowd already buzzing with debate. For weeks, orbital sensors had sketched 3 Atlas as peculiar, yet ultimately understandable. Loaded with carbon dioxide, occasionally showing a pale green tint in edited overlays, with a trailing envelope extending hundreds of thousands of kilometers outward. The light analysis was quirky but decipherable. The form was odd but simulatable. All signs suggested a rare comet, born in unfamiliar environs beyond our system, hurled from a far-off world setup, now slicing through our space on a one-off route. Yet this Martian view displayed blue, not green, not bland, pure blue. That lone color mismatch cracked open divisions in the digital stargazing scene, divisions that grew sharper over time. Lowe's endorsement packed punch since he'd been layering arguments for weeks via his 3 Atlas updates, piling irregularity on irregularity, each solo dismissible, but together disquieting. A solar-facing radiance bucking standard comet traits. Spectral hints of manufactured metal balances. Polarization data straying from familiar comet groups. And this latest, a blue blot from Mars dirt, disseminated via casual networks as formal records stayed bottled up in bureaucratic checks. The source was key. No official NASA bulletin here. No vetted findings in Nature or the Astrophysical Journal. Just an enthusiast's composite tossed on his social platforms, vouched for by a polarizing yet qualified astrophysicist, and promptly challenged. Puzzled over equally by enthusiasts and doubters alike. Imagine the implications if that photo turned out to be genuine. The visible glow on its surface would need to be sufficiently intense for a camera built for daytime rock studies on Mars to pick it up across several shots. This pointed to possibilities like optimal angles for observation, an exceptionally shiny exterior, or perhaps an object that reflected or emitted light way better than your average dusty halo around a comet. The cautious view held that we were likely witnessing sunlight bounced forward from the carbon dioxide-laden envelope that telescopes like JWST and SphereX had already mapped out. The setup lined up perfectly. During the close pass, Mars was positioned just right in the line of view. Layering multiple images could definitely tease a dim, spread-out feature from the background clutter. Yet the bolder theory stirred up real excitement. Suppose the glow wasn't from scattered particles or gas, but from an organized, mirror-like face? What if 3I Atlas wasn't a comet in the classic sense, but an artificial construct meant to mimic one from afar, only showing its real character when probed up close? The crowd split right away, with raw reactions all around. Fans viewed it as proof of the ideas Lowe had pushed from the start. Here was the key evidence, the initial solid sign from Mars of an interstellar guest that could be engineered rather than random. Those combined shots matched the forecast from simulation spot on. A subtle yet clear trace at the precise spot in the sky, emerging only after meticulous handling. Critics dismissed it as glitches, lucky overlaps in time, and the pitfalls of spotting patterns in messy datasets. They flagged valid issues with the data handling. In what way were the images lined up? Which color filters got used in the layering? Could stray cosmic rays or faulty sensor spots have faked a genuine blip there? Lacking the original files, no one else could check it independently, turning that barrier into fresh fodder for debate. The odd hue caught the eye of anyone tuned in. Orbiting observatories with precise spectral analysis had detected carbon dioxide overwhelming the surroundings, mixed with a bit of water vapor and faint traces of metals like neutral nickel and iron. A carbon dioxide-heavy envelope should look bluish. It diffuses sunlight with a flat or faintly green tint, varying by particle size and angle. But blue suggested otherwise. Maybe diffusion from tiny bits, or a gleam off a sleek metal plane, or just a quirk in how Mastcam's sensor grid got treated during the merge. That blue blotch sparked far more puzzles than solutions. And that's exactly what made it compelling. In the space between our anticipated view and this unexpected overlay, a flood of wild theories poured in to claim the empty spot. We have to dig into what went down, not only the picture, but how it got out there. Why choose Mastcam for such a niche scan, and what the tint reveals about the target or the gear itself. Next comes the tougher probe. If this find holds up, what does it say about 3I Atlas's true makeup? And if it's bogus, why did it hit so hard with folks already geared up to spot wonders lurking in the obvious? Part 2. Dissecting an alleged breach. The photo didn't emerge via proper outlets, and that's bigger than it seems. Simeon Schmaus shared his merged Mastcam shots on Blue Sky on October 4, 2025, roughly a day after 3I Atlas's nearest swing by Mars. His update laid out specifics on picking shots, syncing techniques, and the positional forecast he applied to pinpoint the object's spot against the Martian backdrop. Lowe grabbed it fast, weaving it into a medium piece that tied the find to his ongoing tale of 3I Atlas oddities. The shout-out lended a stamp of credibility from the source, despite dodging all the usual checks NASA's Perseverance team puts on shared data drops. This embodied amateur astronomy at its strongest, yet trickiest. Strong because it proved that sharp hobbyists with the know-how could mine public archives for hints that official teams hadn't spotlighted. Tricky because, absent checks from fellow experts on those same source files, we couldn't tell true data from handling errors. Merging shots is a go-to move in sky imaging to drag weak objects from the haze by blending repeated captures. The idea is simple. Erratic static fades out over layers, while actual features build up. Line up 10 views of one area and add them, and the fuzz drops by the square root of 10 as the real stuff ramps up straight. Yet the real challenge hides in the syncing process. Minor alignment issues during frame registration can lead to color fringing, particularly when the subject moves against the starry backdrop. Misregistration of color channels in the stacking procedure might generate unnatural color halos unrelated to the target's actual spectral profile. Even the sparse Martian atmosphere causes chromatic separation that varies at lower altitudes. Moreover, if the target is so dim that it scarcely exceeds the noise floor in single exposures, the risk of confirmation bias intensifies. Observers tend to perceive patterns they anticipate, above all when hunting for a discovery they yearn to confirm. Mastcam-Z wasn't built for such tasks. It's a versatile, zoom-capable multispectral stereo imaging setup on the Perseverance rover's mast, tailored for geological mapping, expansive terrain views, and detailed examinations of rock surfaces. The device features 11 bandpass filters covering visible light through near-infrared, enabling analysis of mineral types and air quality under Martian sun. Its focal length adjusts from 34 mm to 110 mm equivalent, offering versatility for broad contextual shots and focused inspections. Yet, at its core, it's a solar-illuminated geology tool, not suited for deep space photography. It doesn't support extended exposures, precise tracking, or the low-noise sensitivity of specialized astroimaging gear. Standard operations focus on illuminated impact basins and dust-sculpted ridges, rather than elusive stellar objects crossing the dark heavens. The camera's angular coverage and resolution introduce further hurdles. At full zoom, Mastcam-Z captures a broad swath of the sky relative to a telescope's narrow beam. Dim peripheral sources might trigger lens flares or internal bounces. Phantom artifacts emerge in fixed positions dictated by the optics. In prolonged dark frame captures, detector noise generates rogue pixels and radiation strikes that demand meticulous removal in post-processing. Though tenuous, Mars's air still diffuses daylight at night, especially low on the horizon. Airborne particles faintly illuminate under diffused dusk or stellar glow, yielding a fluctuating sky glow influenced by haze levels and line-of-sight angle. These elements collectively render subtle signals open to interpretation. A hazy blotch might represent a genuine find, or merely the overlap of multiple device and site-specific influences coinciding at the forecasted spot for 3i Atlas. The inquiry into raw data swiftly dominated discussions mere hours after the pilfered composite surfaced. Should Schmaus have truly spotted 3i Atlas in Mastcam-Z captures, then theoretically, any researcher accessing identical unprocessed files could replicate the outcome. NASA routinely releases Perseverance's uncooked photos via the project's digital repository, often shortly after capture. However, verification demands precise details on selected frames, their timing stamps, the vehicle's orientation, and pre-stack corrections applied. Lacking this information, external checks turn into random searches. One might sift through scores of nocturnal sky shots from the pertinent period without locating the precise set that yielded the initial blend. And should matching frames emerge yet fail to yield the anomaly, does that indicate a false positive or simply divergent analysis techniques? Other validation routes were proposed and debated openly in the aftermath of the close passage. Satellites circling Mars, including the Mars Reconnaissance Orbiter's HiRISE instrument, Mars Express, and the ExoMars Trace Gas Orbiter, offered advantageous viewpoints for spotting 3i Atlas amid the transit phase. Low highlighted HiRISE as a key resource in his advanced publications, emphasizing how its sharp imagery could estimate the body size by detecting pixel-level intensity spikes. With HiRISE's 30 km/pixel acuity at 3i Atlas's range, a vivid concentrated emitter could overload specific detectors or form a noticeable diffraction pattern, regardless of subpixel dimensions. That said, HiRISE outputs, much like Mastcam-Z's, undergo internal scrutiny prior to dissemination. The interval from data capture to availability might span days to weeks, based on operational demands and evaluation depth. Plausible non-sensational accounts for the anomaly abounded and merited thorough review. Faulty pixels plague CMOS arrays, especially in drawn-out integrations or fluctuating thermal conditions. A defective sensor element precisely at the expected site could mimic the subtle, fixed trace observed in composites. High-energy particles bombard sensors relentlessly, producing vivid ephemeral flares that, Should they repeatedly strike the identical detector site, random chance detections spanning various frames might imitate an authentic celestial object. Particles on the device's shielding pane or within its internal optics could diffuse light intricately, generating subtle rings or sidelong radiances. Artifacts from compressing JPEG or PNG formats for widespread sharing might introduce striping, hue alterations, or false details absent in the original unprocessed sequences. Alignment errors while combining images, especially from shots with minor variations in aiming or focus, could yield border distortions and color edging. Lastly, a true yet incidental distant star positioned close to the forecasted route of 3E Atlas might produce a legitimate stellar signal unrelated to the space wanderer. The azure hue stood out as the most compelling yet dubious aspect. Color calibration choices play a crucial role in RGB compositions. Mascom's unprocessed images record photons in 11 distinct wavelength ranges, which require merging and tonal adjustment to form the sort of accessible RGB visuals that people readily understand. Varying presumptions regarding lighting environments, air permeation, and object traits can drastically alter the hue equilibrium. An analysis workflow tuned for daytime Mars, where the light spectrum gets tinged reddish by air diffusion, could mishandle hue bands and spawn distortions when used on dim nocturnal skies. Minor variations in demisacing the BOF filter grid during initial conversion might cause hue drifts, particularly under weak signal strength and with air path influences. Even on Mars, these can favor scattering violet light based on particulate density and observation angle. A genuinely achromatic or impartial emitter could seem azure if the workflow presumed a warmer setting than what was real. Yet, a more fascinating option emerges, though it demands cautious wording as it dips into conjecture. Should 3E Atlas possess a shiny metallic exterior instead of a scattered particulate envelope, specific calibration choices in processing might skew the hue azureward beneath Mars' dark heavens. Materials such as aluminum or stainless steel exhibit even reflectivity over visible light, bouncing back solar rays without marked chromatic bias. However, if the workflow anticipated a cozy light origin, like for solar Mars shots, and instead met a balanced reflector lit by pure sunbeams bounced from the Martian ground or air, the hue tweak might overcompensate and force a bluish appearance. This remains conjectural and improbable compared to basic handling flaws, but it highlights the urgency for unprocessed sequences and clear procedures to separate true phenomena from device quirks. The hue discrepancy signals a need for verification. We can't derive natural laws from a tinted composite run through obscure workflows and circulated on social platforms. Raw sequences are essential. Independent experts must employ varied handling methods and cross-check outcomes. Spectrographic data from Martian tools, should suitable ones be available, or at least broad-spectrum brightness measures could reveal if the azure shade holds up or stems from artifice. Without such validations, the streak stays true to its label, a haze, an enigma, a tease. Still, the puzzle persists. What if it's authentic? What if, setting aside the hue, Mascom truly recorded 3E Atlas crossing Mars nighttime, vivid and near enough for a ground viewer to spot it via layering? What insights would that offer on its observed luminosity, exterior traits, or orientation to Mars at peak proximity? Such inquiries guide us to consequences tougher to brush off with talk of faulty pixels or file distortions. For if the sighting proves genuine, 3E Atlas shines stronger, nears closer, or gleams more than anticipated. And in celestial studies, luminosity often hints at scale or exposed surface. That leads to the uneasy thought that this visitor could dwarf prior interstellar travelers by far. Part 3. A sequence of quietude and happenstance. The period from October 1st to 7th, 2025, was meant to yield resolutions. It brought inquiries shrouded in hush and heightened by serendipity. Periapsis hit on October 3rd around 1300 UTC, as 3E Atlas swept by at 29 million kilometers from Mars. The detection span stretched a few days before and after, with optimal sightlines from October 1st to 7th. Lowe's advanced publications had built anticipation. He foresaw inputs from assorted Mars satellites, such as the Mars reconnaissance from the high-resolution imaging system on the Sankey orbiter, ESA's Mars Express probe, and the ExoMars Trace Gas Orbiter, observations were anticipated. He pointed out that the Mars-CAM-Z on Perseverance could offer glimpses of the night sky if the team allocated time for it. These sightings, he argued, would provide vital insights into the dimensions, makeup, and shape of One-Eye/Oumuamua, clearing up uncertainties that ground telescopes struggle with because of remoteness and observation angles. Eager observers held their breath. The incoming data stream remained silent, and in that quiet, a storyline started to take shape. Over time, Avi Loeb has built a consistent rhythm in his work, and followers have grown accustomed to the routine. He releases articles that pile up oddities and pose probing queries just before space organizations drop their formal findings. He presents data in a manner that highlights unlikely alignments and shifts from standard norms. He posits artificial origins next to natural explanations, viewing both as equally deserving of scrutiny rather than outlandish ideas needing ironclad evidence. This method has positioned him as both a key voice and a divisive figure. Fans regard him as a researcher bold enough to question established views and tackle tough inquiries. Detractors view it as biased logic and a habit of seeing patterns in random fluctuations. Yet, no matter one's view of Loeb's tactics, his accessible writings build excitement. When he announces that sightings are on the horizon and will settle major debates, the public braces for clarity. If that clarity doesn't emerge as forecasted, rumors surge to bridge the void. The timing of the U.S. government closure only intensified an already brewing tension. A limited federal halt kicked off on September 30th, 2025, impacting optional initiatives, among them certain NASA functions. Outreach teams cut back operations. Routine project tasks got delayed. Timelines for sharing information dragged. Such disruptions weren't novel or shocking. These pauses typically hit outreach efforts harder than essential spacecraft work. The Martian satellites and Perseverance kept running smoothly. Research information kept pouring in and transmitting downward. However, the outward-facing elements, like official announcements and polished photo collections that turn raw signals into engaging stories for the masses, fell silent. Influencers and analysts seized on the closure as a compelling angle. Why did this pause align so neatly with the Oumuamua close approach? Was it pure misfortune? Or could authorities have motives to limit outreach precisely during this key viewing period? To state it plainly, nothing indicates the halt was orchestrated to hide Oumuamua details. Such events stem from legislative funding deadlocks, not targeted project factors. And amid these interruptions, NASA's far-reaching endeavors persist as vital systems. The Mars Reconnaissance Orbiter stays active. Perseverance keeps snapping photos. Information continues streaming to Earth-based receivers and repositories. What lags is the labor-intensive task of selecting, explaining, and distributing that information to everyday audiences. The overlap was happenstance. Still, in an atmosphere thick with conjecture, such alignments turn into foundational blocks for theory-laden tales. Fair or not, the viral cycle unfolded just as online networks intend. A post from Schmaus on Blue Sky rippled over to X, once known as Twitter, where it got reposted and captured in screenshots scores of times. It surfaced in Reddit forums on astronomy and unidentified aerial phenomena, sparking discussion chains that ballooned to hundreds of responses debating origins and meanings. Sites like The Debrief ran with the piece, boosting the Perseverance blurry blot meme through titles that balanced straight news with teasing suggestions. At every step of escalation, fresh viewers, fresh takes, and fresh waves of guesswork emerged, untethered from the precise mechanics of the initial image set. In under 3 days from the photo's debut, it had carved out a shared cultural footprint, separate from debates over whether it showed a real find or a glitch in handling. The blot lived on not only in the pixels, but in the shared mindset of all tracking the saga. And that mindset started pressing for explanations that standard outlets weren't delivering within the anticipated frame. This dynamic echoes past cases. The uncertainty around Oumuamua stretched over months, with early scans hinting at a strangely stretched, rotating body and later non-gravitational thrust readings pointing to uneven gas emissions. Or, in Loeb's debated perspective, a solar sail. The absence of visible coma or debris sparked prolonged arguments over its nature: comet, space rock, or an outlier. Findings trickled forth via drafts and vetted studies as digital groups theorized extravagantly. Oumuamua, the interstellar meteor debris that Loeb's team said they recovered from the Pacific Ocean, traced a comparable path. Early spotting and orbital modeling led to mission preparation, sea-based recovery, and lab examination of metal spherules, which Loeb maintained displayed unusual isotopic compositions. Every phase spanned months, with formal validations trailing Loeb's published articles. Skeptics challenged the readings. Follow-up efforts either flopped or backed rival theories. Yet the storyline's drive, once set in motion, resisted reversal despite growing scientific pushback. Delays in sharing info are typical in intricate observation efforts, and they don't signal a conspiracy. Spacecraft info needs downloading, unpacking, and adjusting. Alignment details require matching with accurate orbital data for the object. Unprocessed images demand bias correction, flat fielding, and compilation into logical visual series. Spectral readings involve wavelength tuning and pulling one-dimensional profiles from two-dimensional sensor grids. This whole process demands time, especially if the viewing strayed from the core mission goals and calls for custom handling. Mars satellites focus mainly on the planet's rocks, air, and weather patterns. Spotting a fleeting interstellar visitor counts as extra research, but it's not why those probes were launched. Top priority stays with Mars findings. The trio of Atlas detections gets processed when experts find spare capacity, which amid a federal shutdown and concurrent project deadlines could stretch to days or weeks instead of mere hours. Still, quiet periods, even if justifiable, breed room for conjecture. The key lesson here is simple yet uneasy. No proof doesn't prove nothing exists, but in a high-profile, intense monitoring operation, lack of updates acts like proof of an issue. Perhaps it's mere administrative drag. Perhaps it's wariness around bold assertions, a hesitation to share early results that could get twisted. Perhaps it's a mix of communication hurdles, the shutdown, mission demands, and internal checks, all teaming up to form a void where people crave quick answers. Or perhaps, and this ventures into the speculation zone, we should note while steering clear of it, the first batches of data revealed something vague or intriguing enough that officials opted for thorough double-checks prior to any announcement. Not to conceal extraterrestrials, but because errors in judgment, whether too much or too little, carry massive fallout. We must probe the hue mismatch closely. So why does the blur show up blue, while all other tools assessing the 3 Atlas instances detect carbon dioxide heavy, neutral to greenish diffuse illumination? That lone color anomaly outweighs nearly every other aspect of this tale, as it's measurable, verifiable with raw data access, and points to either device glitches or novel phenomena. Once we clarify the color, we face the tougher inquiry. If the disclosure holds up, what insights does it offer on the essence of 3 Atlas? Part 4. The green that shifted blue. Conventional sensor views depicted 3 Atlas in tones of green and neutral gray, with a makeup led by carbon dioxide and a shape that elongated mainly toward the sun. The disclosed Mars photo displayed blue. That color clash requires accounting, and the accounting counts because hue reflects physical laws. JWST's near-infrared spectrometer viewed 3 Atlas in late September 2025, gathering detailed spectra of the surrounding gas cloud that pinpointed carbon dioxide as the leading volatile material. The CO2 to water proportion clocked in at roughly 8:1, well above the norm for solar system comets where water leads. This result stood firm, featured in an AR-14 preprint and backed by NASA's Goddard Space Flight Center in their digital research summaries. The carbon dioxide gas cloud intensified toward the sun, with emission rates much stronger on the sunward half than the night side. Water appeared but stayed minor, clustered in a tighter zone close to the core. Such makeup hinted at origins near a carbon dioxide frost boundary, maybe in the distant zones of a star system where CO2 stays icy as water evaporates from prior warmth. Or it pointed to surface ice alteration by radiation, where galactic rays and starlight ultraviolet had selectively stripped away hydrogen-laden substances across eons. In any case, the spectral evidence left no doubt. This was a carbon dioxide-dominant body, not water-driven. Sphere X, NASA's orbital infrared telescope, charted 3 Atlas's sprawling gas envelope in early October, uncovering carbon dioxide markers protrusions stretching far beyond the nucleus, reaching over 348,000 kilometers, highlighted the expansive nature of this phenomenon. Such an expansive envelope indicated robust and ongoing release of material, ruling out any brief outburst or confined stream. The structure displayed wide-ranging outflows aligned with evaporation from the surface or just beneath it, fueled by the sun's warmth. This matched precisely the behavior anticipated for an authentic comet as it neared its closest solar approach. Observations from SphereX enhanced the detailed spectral analysis from JWST by adding positional details to the chemical assessments. Combined, these findings confirmed that 3I Atlas was enveloped in a vast shell of carbon dioxide, vapors, and particles, detectable over a broad region of the inner solar system. Images from the Hubble Space Telescope uncovered a distinctive shape, though not entirely without precedent. The standout element was a hazy radiance facing the sun, with a backward-pointing tail that leaned toward the sun instead of trailing away. Traditional comets exhibit backward tails formed by dust and charged particles driven outward by solar radiation and wind. Those sun-pointing extensions arise from the observer's perspective and the spread of particles along the comet's trajectory. Viewing the orbit almost sideways can make earlier ejected dust seem directed sunward, despite actually lagging behind. In the case of 3I Atlas, this setup appeared, but with a dramatically elongated proportion. Researcher Lowe and colleague Eugene Quito observed that the sun-facing arm was roughly 10 times its breadth, forming a slender, pin-like form in enhanced views. Simulations indicated this stemmed from uneven venting from the sunlit side, where particles and gases escaped mainly from sun-exposed areas. The arrangement was peculiar, yet it fit within the established principles of comet dynamics. Regarding the hue of a carbon dioxide-dominated envelope, matters turn nuanced. Pure vapors lack visible coloration. We detect them via specific emission or absorption signatures, rather than broad reflected light. The appearance of a comet comes from sunlight bouncing off tiny dust motes in the envelope. That reflected hue hinges on particle dimensions, makeup, and how scattering varies by wavelength. Carbon dioxide alone doesn't yield green tones. Numerous comets look greenish due to glowing from C2 molecules, which emit vivid green bands near 510 nanometers under solar ultraviolet excitation. Spectra of 3I Atlas published so far lack prominent C2 signals. Without such lines, the scattering from dust in a carbon dioxide-heavy environment should yield a neutral or faintly ruddy shade, akin to sunlight adjusted by particle traits. Certain blended images might add a subtle green cast if software boosts faint glows. However, vivid, oversaturated blue isn't typical. The azure blur in the unauthorized image release thus stands out scientifically. Blue wavelengths scatter more readily from minuscule particles than red ones. This explains the blue vault of Earth's atmosphere and the bluish veil over far-off peaks in misty air. Such scattering prevails when grains are far smaller than light's wavelength. Theoretically, if 3I Atlas's envelope held an atypical abundance of ultrafine dust or haze, and Mars's viewpoint favored forward scattering, a blue element could emerge. Yet, JWST and SphereX data revealed no evidence of prevalent submicron sizes. The particle distribution they derived aligned with standard comet debris, ranging from submicron to millimeter, with bulk in coarser bits. Nothing points to why a carbon dioxide-rich envelope would scatter sunlight blue. Thus, we circle back to equipment and handling factors. A tool like Mastcam-Z, built for daytime rock analysis under Mars's lighting, employs color adjustments tailored to that setting. The red Martian ground stems from iron-rich dust, while daytime skies carry a pinkish-orange tint. The device's balancing routines aim to depict terrain in interpretable hues for experts. Aiming it at a dim celestial object after dark strays well beyond its design. The color tuning might just mismatch. Should the system presume a reddish light source and face a more balanced one, the adjustments could swing too far, shifting the perceived tone blueward. Mundane as it sounds, this remains the prime suspect. Another possibility, purely conjectural, points to aggressive noise reduction or improper channel balancing during the image stacking. Suppose the red channel exhibited more noise than the blue and green ones in the separate exposures. An expert could opt to reduce its influence to prevent inserting false patterns. Alternatively, if the captures used varying filter setups before merging into an RGB composite, those selections might not align perfectly with actual hues. The Mascom system's filters feature narrow spectral ranges that don't precisely match conventional RGB bands. Blending them to form an eye-friendly color picture demands choices on channel weighting. Such choices can yield varying results, particularly for dim objects with low signal-to-noise ratios. This idea of channel imbalance can be verified with the original files, if available. Without them, though, it's just theory. The most improbable explanation, yet one circulating in conversations and thus needing mention, suggests a shiny metallic exterior. Suppose 3i Atlas isn't a hazy, scattered coma but a solid, organized body with a mirroring surface. Then, specific white balance settings might shift the hue bluard in the Martian nocturnal environment. Metals typically show even reflectivity throughout the visible spectrum. They won't look blue on their own unless layered or patterned to favor shorter waves. Stainless steel appears silvery gray. Aluminum does too. Buff titanium follows suit. However, if the software anticipated a ruddy light source but met flat reflectance, the adjustment could tip the final image toward blue. This scenario is feasible in principle, but it hinges on dual conditions. First, 3i Atlas would need to be a gleaming construct, not a nebulous coma. Second, the workflow must have botched the color tuning just so, turning neutral input into a blue anomaly. These overlapping demands render the notion tenuous, though not entirely dismissible. In essence, the situation is blunt and unsettling. We can't draw physical conclusions from a tinted composite run through obscure techniques and released via unofficial routes. The discrepancy between the azure Martian blotch and the bland to greenish views from orbital sensors raises alarms, wordplay included, calling for replication using unprocessed shots. Independent experts must handle the same inputs with clear, recorded procedures. Multiband data from Mascom Z would help, letting us rebuild the spectrum and assess if the blue shade is genuine or a glitch. Verification from additional Mars assets, grabbing info during the approach phase, is essential. And we must openly admit that, sans these validations, the blotch reveals more about handling than the entity itself. Setting color issues aside, let's suppose the sighting is authentic. Imagine Mascom truly recorded 3i Atlas crossing the Martian dark side at the forecasted spot. Subtle yet detectable, emerging only via meticulous layering, but indisputably visible. What follows? That inquiry ventures into tricky ground, as astronomical luminosity usually ties to scale or shininess. If 3i Atlas shone brightly enough for a planetary camera to spot it from 29 million kilometers away, it must be larger, nearer, or more luminous than any interstellar comet should be. This circles back to unavoidable ramifications. Section 5. The leak's meaning, assuming validity. Observed surface luminosity isn't trivial. It's a hard limit weaving together output, separation, and angle into binding outcomes. If Mascom Z picked up 3i Atlas via accumulated exposures, the thing was luminous, sprawling, or angled just right for a standard imager to tease it from the Martian gloom. That idea packs several realities, demanding precise separation. The cautious view holds that the combined glow depicts the coma, the vast gas and dust sheath already verified by JWST and SphereX. Cometary sheets can be incredibly spread out, diluting light over broad sky areas while total output remains strong. Yet they can also show brightness boosts in key orientations, especially forward scattering setups, where sun rays off particles aimed straight at us. The Perseverance pass positioned the rover ideally to view 3i Atlas's sun-facing side, the zone with ramped CO2 venting noted by JWST and the stretched anti-tail seen by Hubble. If Mars were positioned in the direction of forward scattering, the visible surface luminosity of the coma might have been substantially higher than what was observable from Earth. This aligns perfectly with standard cometary dynamics. It demands no unusual makeup, no organized outer layer, no artificial features. simply the effects of geometry and particulate light scattering at work. Yet, this explanation faces challenges. The MOSCAM-Z instrument isn't well suited for detecting dim, spread-out emissions. Its sensor fluctuations, low-frequency noise, and background signals are tuned for brief shots in intense light, rather than extended exposures of subtle, hazy features. Even when combining multiple images, extracting a broad coma from the background demands that its per-pixel intensity surpass a certain baseline. If the coma of 3i Atlas was as thinly distributed as indicated by the SphereX survey, dispersing carbon dioxide glow over hundreds of thousands of kilometers, then at Mars's range, the intensity would likely have been negligible, falling short of MOSCAM-Z's effective sensitivity threshold, no matter how many frames were stacked. The emergence of any signal, assuming it's genuine, points to either a more focused coma than the wide-area survey implied, or an entity with greater inherent luminosity than a standard hazy gas cloud. The hypothetical view shifts toward a shiny or patterned exterior as opposed to a scattered vapor sheath. Should 3i Atlas feature a dense, mirror-like outer shell, say, a metal casing or layer, its observed radiance would behave far differently from a comet's envelope. Such a gleaming orb or oval would redirect sunlight effectively from its sunlit side, focusing the glow into a narrow viewing angle instead of diluting it over an expansive misty halo. At a distance of 29 million kilometers, the surface intensity of this kind of body could outshine a diffuse coma by factors of 10 or more. That would render it visible to a device like MOSCAM-Z, even under suboptimal viewing setups. The viewing angle plays a crucial role. If Mars caught 3i Atlas at an optimal phase where mirror-like reflection beamed sunlight straight at the rover, the luminosity could surge sharply. This perspective means setting aside the idea that 3i Atlas is essentially a comet and considering it might be an altogether different phenomenon, one shaped by design rather than natural rock formations. In his online articles, Lowers tackled the scale issue head-on, proposing a core diameter of at least 5 kilometers based on luminosity limits and deviations from gravitational paths. His logic links various data points into a logical sequence. The object's standard magnitude, the luminosity at a fixed separation from both the sun and viewer, limits the combination of dimensions and reflectance. Assuming a standard cometary reflectivity of about 4%, where the surface bounces back 4% of incoming sunlight, the recorded luminosities point to a span of several kilometers. The orbital drift beyond simple gravitational pull, caused by gas ejection propulsion, offers another check. For a specific ejection rate derived from envelope luminosity, reduced mass would yield stronger drift. Yet the detected drift is modest relative to 3i Atlas's brightness, which Lowers interprets as evidence of substantial mass. Pairing that mass with average cometary density yields considerable bulk. Thus, the 5 kilometers figure emerges. He converts this to 33 billion tons, a figure designed to highlight the immense proportions involved. A true 5 kilometers span for 3i Atlas would elevate it beyond prior interstellar intruders. Oumuamua's projected lengths reached 100 to 200 meters along its major axis, a modest size by comet or asteroid measures. 2I/Borisov clocked in at about half a kilometer wide, akin to minor solar system comets, but nothing extraordinary. An interstellar visitor of 5 kilometers would stand out hugely, suggesting either remarkable fortune in spotting such a hefty wanderer or that sizable interstellar bodies occur more frequently than the sparse tally from just 2 earlier finds implies. This raises a puzzle in discovery rates. If 5 kilometers interstellar objects traverse the inner solar system often enough for us to snag one within a handful of survey years, then why the absence of smaller counterparts? Surveys naturally spot big, vivid targets over tiny, dim ones. Thus, 100-meter interstellar travelers ought to swarm in numbers far exceeding kilometer-class ones. We'd expect to have log scores of Oumuamua-sized objects before nabbing a lone 3i Atlas-sized giant. Our failure to do so hints that either the dimension assessment is off, or the distribution of interstellar objects defies our expectations in surprising ways. Assumed or that 3i/Atlas isn't just some arbitrary entry in a statistical sample, but rather chosen for particular traits. The utilization of Mars versus orbiter resources turns pivotal in clearing up these uncertainties. In his writings before the flyby, Lowe suggested that the Mars Reconnaissance Orbiter's high-rise camera provided distinctive limitations due to its resolution at 3I/Atlas's range. High-rise captures Mars terrain at about 30 centimeters per pixel from a low orbit. However, when directed at an object 29 million kilometers distant, the practical pixel size expands to roughly 30 kilometers per pixel. That might seem pointless for fine details, yet it's valuable for assessing point source luminosity. Should 3I/Atlas be a tight reflective body instead of a spread-out coma, and sufficiently luminous, it might overload specific high-rise pixels or generate a detectable point spread function that disperses light over several pixels. Through evaluating which pixels illuminated and their intensity, experts could determine if the emission stemmed from a broad scattered origin or a concentrated high-brightness entity. This demands meticulous calibration and simulation, but fundamentally, the information is available or ought to be if high-rise truly targeted it during the flyby period. The purported Mars surface spotting, assuming it's genuine, heightens the importance of these orbiter scans. If Perseverance's basic camera managed to capture 3I/Atlas via image stacking, then HiRISE, boasting advanced lenses and photography prowess, definitely should have spotted it with proper aiming. The lack of updates from HiRISE and fellow Mars orbiters right after closest approach thus holds significance. Perhaps they skipped observing the object, which seems odd considering the detailed preparations and widespread excitement. Or maybe they did capture it, and the results are undergoing analysis and confirmation prior to disclosure, or they recorded it, but encountered findings so unclear, intriguing, or intricate that officials opted to withhold announcements until they grasped the implications. None of these scenarios confirm the essence of 3I/Atlas, yet they collectively suggest one outcome. The Mars flyby transcended typical comet monitoring. This occasion stood out, pushing it past usual protocols. We're poised on the edge of narrative shifts. The alleged leak, if authentic, shifts from an oddity to a crucial evidentiary element indicating that 3I/Atlas defies our prior assumptions. Yet prior to stepping over that line, we must pull back and scrutinize the entity on its own, separate from any disputed photo. What insights do established scientific records offer? What trends appear when viewing 3I/Atlas not as a standalone enigma, but as our third interstellar guest under examination? The peculiarities in its orbital plane, the composition that deviates from solar system norms, the polarization data outside familiar categories, the shape extending sunward in manners requiring interpretation. These aren't leaks, whispers, or data glitches. They represent documented, reviewed, or at least preprint observations from premier tools run by organizations uninterested in stirring debate. Assembled, they form an image that's deeply unsettling. Irrespective of one's stance on artificial origins, they depict an entity that defies our standard predictions for interstellar arrivals. That entity and its ramifications are our focus next. Part 6. The 5 Degrees Enigma. Intentional or coincidental? Picture hurling a dart at a world map from the far side of a room with eyes covered. Then picture that dart, improbably, striking within 5 degrees of the equator. This analogy falls short since you at least directed it toward the map's vicinity. 3I/Atlas entered from interstellar voids without cause to favor our planetary disk. No advance awareness of our world's path. No tie to the level plane shaping the solar system's design. Nevertheless, its path aligns within 5 degrees of the ecliptic, the plane encompassing Earth's orbit and most other worlds. A vibe computed the odds of such a coincidence purely by chance, yielding about 0.2%, or roughly 1 in 500. This figure stems from his model based on presumed random distributions of interstellar objects' approach vectors. Approach that estimate cautiously, as biases in selection and limited sample sizes can exaggerate apparent unlikelihood. Still, under restrained premises, the coincidence warrants scrutiny. The trajectory details are openly accessible and cross-checked via various monitoring networks. 3I/Atlas traces a backward path, signifying motion counter to the PLA. The path of this interstellar visitor as it orbits the Sun reveals a notably close alignment with the ecliptic. Its orbital tilt, defined by the angle between its path and the ecliptic plane, hovers around 4.9 to 5 degrees, varying slightly based on the specific ephemeris model consulted. By contrast, comets originating from the Oort cloud in our solar system typically follow paths with inclinations scattered randomly from 0 to 180 degrees, following an even spread. These long-period wanderers exhibit no bias toward the ecliptic plane, owing to the Oort cloud's spherical shell of frozen remnants encircling the Sun at enormous distances. Interstellar space, under standard assumptions, ought to be even more uniformly distributed in all directions. Debris expelled from distant star systems carries no imprint of our solar setup's layout. Thus, their entry angles should cover the full celestial sphere without favoritism. A trajectory hugging the ecliptic so closely stands out as improbable on statistical grounds. Yet improbable doesn't equate to impossible, and a 5-degree deviation isn't precisely zero. To grasp the implications of this setup accurately, consider the spatial arrangement. A dead-on ecliptic entry would be so anomalous as to suggest artificial origins. But a 5-degree offset remains odd without crossing into the implausible. It situates 3I/Atlas's route within a wide band encircling the solar system's disk of planets, as opposed to a haphazard slice across full 3D volume. This nuance is crucial, since our gut feelings about chance events are often unreliable. We're wired to spot patterns in chaos, frequently mistaking random outcomes for intentional patterns. That 5-degree tilt could simply mark the edge of a probability curve, a rare but permissible alignment among countless possibilities. Alternatively, it might hint at intentional engineering, a flight path optimized for brush encounters with key worlds while keeping the inbound vector from offering Earth prime viewing angles at first sighting. This idea, dubbed the delivered trajectory hypothesis, merits unpacking as informed conjecture. Imagine crafting an interstellar scouting mission to probe a star's planets. You'd engineer the probe's route to swing near several bodies in one go, boosting data yield per fuel expenditure. Our ecliptic hosts not only Earth, but also Venus, Mars, Jupiter, Saturn, and the rest of the giants, all clustered within a narrow angular band. Matching that plane enables gravitational slingshots to multiple sites using just inertial motion, no mid-flight tweaks needed. Indeed, 3I/Atlas zipped by Venus at about 0.03 AU on September 5, 2025, enduring intense solar warmth that probably spurred vigorous vapor release. It skimmed Earth at 1.23 Australian dollars on September 27. Mars came next on October 3 at 0.20 Australian dollars, sparking the controversial leaked Moscamzy image and a prolonged observation push. And it's set to graze Jupiter on March 16, 2026, at roughly 1.9 Australian dollars. For such planetary flybys crammed into half a year, a route slicing through the inner system with uncanny precision. The skeptical perspective reigns in the excitement with basic math. Having spotted just 2 interstellar intruders before, 1I/Oumuamua and 2I/Borisov, we lack the data to pin down typical behavior. Oumuamua entered at about 28 degrees inclination, tilted off-plane, but far from edge-on. Borisov arrived at around 44 degrees, steeper yet still not fully decoupled from the solar layout. A pair of examples hardly sketches a trend. 3 offers marginal improvement. We could be witnessing an emerging trend, with interstellar arrivals favoring ecliptic proximity within 30 or 40 degrees due to unseen factors like galactic tides or the interstellar medium's layout. Or it might be sheer luck. 3 random draws bunching up in a way that catches the eye, devoid of deeper meaning. Sorting truth from fluke demands tracking scores or hundreds of such travelers to chart their entry vectors. We're miles from that threshold. Still, the delivered trajectory notion picks up steam when you stack the 5-degree fit against the mounting oddities ahead. Alone, a near-ecliptic path piques interest but doesn't prove anything. Pair it with the schedule yielding swift close shaves at Venus, Earth, Mars, and Jupiter. Toss in a shape directing glow and particles sunward instead of evenly outward. Blend in composition that defies familiar comet profiles. Mix with polarization data straying from established comet groups. And top it off with the intriguing, though unverified, Hint from a Mars snapshot leak. A surface glare brighter than expected from hazy envelope simulations. Each a single unusual trait might get brushed off as coincidence. Yet the accumulation, the convergence of several improbable characteristics in one entity, is what pushes beyond everyday interpretations. That's the build-up Avi Loeb has been constructing in his published writings, and it's the aspect we must address forthrightly, regardless of whether we end up discarding the idea of artificial origins. The positioning along the ecliptic brings up yet another key point that deserves clear mention. Should the path of 3 Atlas have been chosen deliberately instead of haphazard, its incoming path was likely chosen too. The entity entered from a particular sky sector, defined by exact right ascension and declination, linking to a precise bearing in galactic terms. In the scenario of a deliberate interstellar craft aimed at our solar system, the departure site would align with that entry path, extending back into distant time and space where the route traces rearward through the cosmos. Experts have mapped out that reverse path, adjusting for the galaxy's spin and the sun's drift across the local interstellar cloud. The starting location points broadly toward the Triangulum constellation, though with vast uncertainty in position since the journey's start time remains unknown. At its observed speed of about 29 kilometers per second against the sun, a 10,000-year trip would place its birthplace roughly 2.9 light-years distant, right in our closest stellar vicinity. For a million-year voyage, though, the origin shifts substantially owing to the varying spin of the galactic disk. Lacking the launch timing, we can't nail down the exact source, but the path doesn't align with any standout star system we've noted for planets or peculiar traits. The starting point seems ordinary, based on what we know now, suggesting either an overlooked intriguing origin or a route that wasn't a direct line from start to end. Shape forms just one element in this pile of improbabilities. On its own, it's intriguing but not definitive. When paired with the 6 other quirks Loeb outlined, it forms a pattern urging us to seriously consider that 3 Atlas deviates from standard interstellar comets, if those even qualify as standard. Next, we delve into that statistical pile of unlikelihoods. It's here that arguments for the extraordinary grow tougher to wave away with talk of luck or observational biases. With 7 separate oddities, each rare on its own yet all clustered in one item, this isn't mere chance in a game of dice. It points to either a deep flaw in our grasp of interstellar object dynamics or to an item engineered to act outside nature's norms. Part 7. The Stack of Statistical Improbabilities. In his essay recapping the Mars flyby, Avi Loeb highlights 7 distinct peculiarities setting 3 Atlas apart from what we'd expect of a typical interstellar comet. He presents this from his angle as a searcher for signs of artificial beginnings. Conventional astronomers reviewing the identical observations might spotlight other traits or view the quirks as broadening our view of comet variety, not undermining natural explanations. Still, Loeb's roster offers a solid framework for exploring what renders 3 Atlas truly peculiar. Whether you see the peculiarities as evidence of design or merely rare natural forms, the close ecliptic match we discussed earlier, low probability per Loeb's math, possibly attributable to detection biases or limited samples, stands out enough to demand notice. The schedule amplifies this spatial curiosity. 3 Atlas didn't merely skim the ecliptic plane. It followed a course yielding near passes by Venus, Earth, Mars, and Jupiter over a mere 6 months from September 2025 to March 2026. Such a bunching of planet grazes isn't ruled out by physics in random cases. Any path somewhat synced with the ecliptic must weave near various planets, given their shared orbital flatness. Yet the precise layout and schedule cramming for such passes into quick sequence calls for attuned entry speed and angle. Typical near-ecliptic paths would skim over or under planetary lanes, slicing the plane where no worlds currently sit. That 3 Atlases crossing synced with several planet spots suggests either timely fortune or intent. Loeb pushes for the second. Doubters lean toward the first, pointing out that our spotting tools favor interstellar visitors swinging by Earth, skewing finds toward close approaches. Each side holds validity, and teasing them apart calls for broader population studies. We lack certain observational data at present, Explaining the sunward glow becomes more challenging beyond basic geometric models. Images from the Hubble Space Telescope in mid-September 2025 unveiled the intricate structure of 3I/Atlas in remarkable clarity, depicting a hazy extension oriented toward the sun instead of pointing away. Conventional comets exhibit anti-solar tails, formations driven away by solar radiation pressure and the interplay of solar wind with the ionized gas envelope. Certain comets also feature anti-tails, apparent forward extensions arising from the line-of-sight alignment that reveals the dust trail in profile. In the Hubble study, the sun-facing protrusion of 3I/Atlas was interpreted as daytime gas release combined with a faint anti-solar tail, aligning with uneven venting from the sunlit side of the nucleus. Lowe and his colleague Eugene Quito noted that during the HST imaging period, Earth sat roughly 10 degrees from the sun, 3I/Atlas alignment, positioning us to observe the body almost edge-on. Their calculations indicated the sunward arm extended about 10 times its breadth, suggesting an exceptionally slender form once accounting for foreshortening. While rare, such patterns appear in prior comet studies, where uneven gas release stems from localized active zones on the core. What sets 3I/Atlas apart is the blend of this sunward boost, the striking elongation, and the CO2 heavy makeup we'll examine next. The predominance of carbon dioxide in the gas envelope stands as the strongest confirmed oddity, backed by JWST observations, the benchmark for chemical breakdowns. Infrared readings from late September displayed prominent CO2 spectral features, yielding a CO2 to H2O proportion of around 8 plus or minus 1. This dwarfs the norm for solar system comets, where water ice typically leads and CO2 makes up just a handful to perhaps 30% of the volatiles. CO2-rich bodies do occur, like Comet 29P/Schwarzmann-Watchman 1, renowned for its CO2-triggered flares, though they're uncommon. Such elevated levels imply 3I/Atlas originated where CO2 stayed solid as water ice dwindled, possibly beyond the CO2 frost boundary in its home system or due to long-term erosion by cosmic rays and ultraviolet light favoring water loss. Each possibility holds merit, yet both demand specifics on its stellar birthplace and ejection timing to test properly. The iron-poor, nickel-abundant makeup marks where Lowe's perspective turns boldest and sparks the fiercest debate. In his article, Extreme Nickel Production, he spotlighted neutral nickel spectral signals detected over heliocentric ranges from about 3.14 Australian dollars down to 2.14 Australian dollars. Companion iron signals, usually paired with nickel in comet atmospheres, vanished closer than roughly 2.64 Australian dollars. Lowe viewed this as evidence of unusually elevated nickel-to-iron levels in the released gases, deeming it extraordinarily deviant from solar system norms and 2I/Borisov. Spotting neutral nickel and iron in comets is a fresh finding, with initial reports emerging just in the past 10 years. These metals in gaseous form baffle experts, as evaporating tough elements demands intense heat beyond what usual ices provide even at closest solar approach. Current theories point to breakdown of metal-organic compounds via photodissociation or evaporation of metal-laden particles warmed by sunlight. Yet the puzzle persists. Why would nickel outshine iron in 3I/Atlas's envelope, despite iron's greater prevalence in cosmic abundances? Lowe posits the odd ratio hints at artificial sources, like engineered alloys with boosted nickel content. Though this builds on partial evidence and invites skepticism, the raw spectral data itself is solid, if open to dispute. Deep negative polarization delves into niche expertise. This technique gauges the linear polarization of an object's light, where the electric field vibrates along a favored axis over isotropic patterns. Comets induce polarization in reflected sunlight via dust particle scattering, influenced by particle dimensions, forms, materials, and observer angles. Phase angle polarization, the span from sun through comet to viewer, traces defining profiles that group comets into categories. Measurements of 3I/Atlas's polarization profile at varied phase angles on route displayed traits unlike those of established solar system comet groups. Comets, In particular, it displayed greater negative polarization at low phase angles compared to standard comets. Yet this remained compatible with models of natural dust particles, provided one permits atypical characteristics in those grains. The preprint on polarimetric images that detailed these findings presented them as broadening the recognized variety in cometary dust without suggesting any artificial sources. However, there's a boundary to such variety. If each interstellar body we observe deviates from the norms set by countless solar system comets, eventually we must question whether invoking greater diversity is overreaching as an explanation. The discrepancy between brightness and acceleration is more nuanced and demands insight into how non-gravitational influences alter comet paths. As a comet releases gases, the ejected material, gas and dust alike, imparts momentum. Should the outgassing be asymmetric, focused on one side or particular jet paths, the resulting thrust mimics a small rocket, nudging the comet away from a strictly Keplerian trajectory. This extra acceleration varies inversely with the object's mass for a fixed outgassing intensity. Thus, smaller comets show bigger shifts from pure gravitational paths than their larger counterparts with equivalent activity. By gauging this non-gravitational push and approximating outgassing levels from the coma's luminosity, researchers can limit estimates of the comet's mass and, assuming a certain density, its dimensions. 2I/Borisov revealed only modest non-gravitational acceleration relative to its glow, which, per Loeb's examination, points to substantial mass. Such mass suggests either considerable size or exceptionally high density. Loeb opts for the former, leading to his projection of a 5 kilometers diameter. Detractors contend that linking coma luminosity to nucleus mass is shaky, since brightness ties to dust output, which doesn't reliably indicate the volatile reserves or overall mass of the core. The conflict persists, but resolving it hinges on the uncertainties one tolerates and the premises one favors. 7 peculiarities, each singly accountable through natural mechanisms if one accommodates unusual genesis scenarios. Odd makeup or uncommon, yet feasible shapes. Alignment with the ecliptic might just be luck. Timing of planetary flybys could stem from observational bias. The glow toward the sun may arise from asymmetric venting seen sideways. Dominance of CO2 could trace to origins near a CO2 frost boundary or solar radiation effects. The nickel-to-iron pattern might reflect peculiar grain photoreactions. Negative polarization could simply extend the spectrum of natural dust traits. Limited acceleration amid strong brightness might indicate hefty mass or variable dust-gas proportions. Individually, none of these interpretations stretch credibility. Yet demanding all occur together in one entity piles up improbabilities into an unstable edifice. Loeb's approach highlights this pileup to contend that the cluster of oddities taxes the natural explanation past the limits Occam's razor would endorse. Conventional astronomers counter that we've only spotted 3 interstellar visitors in total. Nature's variety is immense, and bold assertions need robust proof. Each stance holds merit, explaining why 2I/Borisov has ignited such contention in discussions over parsing unclear observations. The nickel issue merits separate scrutiny, as it's the irregularity most suggestive of industrial or design chemistry. If seeking clear indicators that 2I/Borisov isn't natural, the ratios of metal emissions are prime targets. And that's our next focus. Because this object's chemistry isn't merely odd, it's revealing. Section 8. The Nickel Dilemma. Nickel sans iron mirrors the composition markers of man-made stainless steel blends, where nickel is intentionally incorporated to boost rust resistance and structural strength. Avi Loeb voiced this parallel outright in his Medium pieces, a notion echoed by sources like The Debrief in reporting on 2I/Borisov data. It's a striking angle, one that calls for distinguishing raw observations from potential inferences. Loeb's piece on extreme nickel output recapped spectral findings across 2I/Borisov's approach from roughly 3.14 Australian dollars, where neutral nickel emissions were first noted, to 2.14 Australian dollars nearing perihelion. Nickel persisted reliably throughout, manifesting as telltale lines in the visible range from about 5,000 to 6,000 angstroms. These arise when neutral nickel atoms in the coma soak up solar UV light and re-emit it visibly at wavelengths fixed by nickel's atomic makeup. Iron, with its parallel emission features in nearby bands, went undetected in the spectra gathered belt around 2.64 Australian dollars from the Sun. The observations suggest that iron might not have been abundant in the gases released from the comet, or alternatively, that iron and nickel emerge through distinct processes triggered at varying distances from the Sun. To better understand this enigma, let's connect it to basic chemical principles relevant to these solar distances. The Sun's heat raises the surface temperature of a comet's core to roughly 200 to 300 Kelvin, influenced by its reflectivity and heat retention. At those levels, it's possible to directly turn water ice, carbon dioxide ice, carbon monoxide ice, and other volatile ices that make up comet cores into vapor, yet far too cool to evaporate solid nickel or iron metals outright. Nickel liquefies at 1728 Kelvin, while iron does so at 1811 Kelvin, with boiling points even more extreme. Therefore, the neutral nickel and iron atoms detected in comet tails don't stem from large-scale melting of the core's metals. Rather, they probably arise from metallic compounds in organics, atoms of metals integrated into organic frameworks, or tiny dust particles with metallic components that heat up dramatically, far beyond the core's average, due to intense solar energy absorption. Detecting nickel and iron emissions in comets is a fairly new development. The first solid evidence came in 2019 from studies of the interstellar comet 2I/Borisov, followed by verifications in multiple comets within our solar system. Previously, experts assumed that durable metals like these wouldn't show up in comet envelopes because the conditions were insufficiently hot. These findings prompted a fresh look at comet composition and sparked ongoing discussions about how metals get liberated, as explored in current research. Many theoretical frameworks suggest that sunlight breaks down compounds such as nickel carbonyl or iron carbonyl, which can vaporize at far milder temperatures than the elements alone and then fragment under UV light to free the metal atoms. A different idea is that minuscule grains with embedded metals absorb focused sunlight, spiking to extreme heats that enable metal evaporation right from the particle exteriors. What sets 3 Atlas apart is not just the nickel detection, now observed in various comets, but the nickel-to-iron proportion and its variation as the object moves closer to or farther from the Sun. In cosmic makeup, the proportions of elements forged in stars and distributed across space indicate iron exceeds nickel by about 17:1. Iron ranks as the top heavy element universally, trailing only oxygen, silicon, magnesium, and a handful more. Nickel appears often enough, though clearly scarcer than iron. Materials in our solar system typically mirror these universal ratios, barring any sorting effects from particular events. Stony fragments from space, representing the rocky stuff that formed worlds and rock piles, display iron-nickel balances aligning closely with cosmic norms. As ancient relics born in the chilly outskirts of the young solar system's disk, comets ought to exhibit cosmic-like or very similar metal proportions in their makeup. Should 3 Atlas reveal nickel without detectable iron, or nickel vastly outpacing iron, a few explanations arise. First, the original stuff that coalesced into the comet could have been chemically sorted, boosting nickel over iron. Say, if its birth setting favored the buildup of nickel-rich solids, stranding iron in vapors or forms that escaped incorporation into the core. Second, the ways metals escape into the tail might differ for nickel versus iron, possibly due to their ties in unique molecular forms or dust types that release or shatter under varying heat or light intensities. Third, detection biases in the instrument's spectral bands and precision might favor spotting nickel over iron, yielding a false impression of unevenness that misrepresents the true blend. Fourth, the substance could deviate from typical comet fare, perhaps due to deliberate modification or design that tweaked metal balances. Low positions this last idea as plausible, drawing parallels to Earth-made industrial blends where nickel gets mixed into iron for rust-resistant steels, high-performance alloys, and similar tough substances. He isn't proposing that 3 Atlas is some fabricated hunk of welded stainless from an extraterrestrial workshop. Instead, his point is nuanced. If it were a crafted artifact built to endure voyages between stars and brushes with the sun, its skin or framework might use alloys selected for heat tolerance, radiation shielding, and structural durability, leading to nickel-iron mixes optimized for function rather than echoing natural cosmic distributions. The inherent elemental makeup of their originating surroundings. As these substances vaporize or release gases due to solar radiation, the expelled particles would transport those modified proportions into the surrounding haze, where spectral analysis could spot them as deviations from standard norms. This remains purely hypothetical, marked as such, yet it's a hypothesis ripe for testing. Should 3I/Atlas keep displaying nickel-dominant outflows as it passes closest to the sun and heads outward, and if improved resolution in spectra verifies the scarcity or minimal presence of iron, the argument for an atypical makeup gains traction. Should subsequent sightings reveal iron emerging at varying distances from the sun or viewing angles, that would bolster the idea that nickel and iron originate from distinct material types with separate heat release points. If lab experiments on similar substances, like organometallic compounds or grains containing metals, exposed to ultraviolet radiation and temperature fluctuations mimic the detected spectral features, that could offer a straightforward explanation. The evidence isn't definitive so far, explaining why Loeb's bold perspective sits alongside conventional restraint. This connects to Loeb's prior research on IM-1, the interstellar meteor whose remnants his group recovered from the Pacific seabed. Examinations of metallic spherules gathered on that mission suggested odd elemental proportions and isotope patterns, which Loeb saw as signs of artificial creation or, at minimum, origins beyond our solar system. Other labs reviewing comparable spherules challenged those views, contending the compositions aligned with Earth-based pollutants or wrongly categorized cosmic particles from ordinary meteor friction. The debate surrounding IM-1's results has bred doubt among peers toward Loeb's assertions on 3I/Atlas's nickel traits, seeing it as a recurring tendency where he spots manufactured traces in findings others attribute to ordinary differences. Such doubt is reasonable, though it doesn't undermine the spectral data per se, sourced from reputable facilities and shared via publications or preprints for expert review. How might upcoming data settle the nickel issue? Spectra with better clarity over broader solar distances and observation perspectives could clarify if the nickel-to-iron balance holds steady or shifts by viewpoint. Observations spanning multiple wavelengths, such as in the ultraviolet, might uncover faint iron signals overlooked in visible light. Controlled tests on emissions from comet-like samples could benchmark anticipated natural proportions, and assessments of additional comets, both local and from afar, should we spot more, might determine if 3I/Atlas stands alone or joins a group of nickel-heavy bodies. These checks remain pending, leaving the nickel puzzle unresolved, intriguing, and wide open. The spectral oddity merges with structural peculiarities to form a tougher-to-decipher overall image than the quarks separately. The nickel enigma signals chemically atypical releases from this body. The sunward jet highlights geometrically irregular ejection and spread of matter. Combined, they suggest either unfamiliar physical mechanisms or deliberate construction we're reluctant to entertain fully. We now shift to the sunward jet and its ramifications, as that form isn't merely odd, it's oriented. And orientation in the natural world often stems from intense evolutionary forces or intentional crafting. Part 9. The Sunward Jet and the Shadow Trail. In mid-September 2025, the Hubble Space Telescope imaged 3I/Atlas, yielding visuals that sparked prolonged debate and scrutiny. The shape caught the eye right away for those versed in standard comet forms. Dust and vapor stretched mainly sunward, forming what experts term an anti-tail, a forward extension contrasting the usual dust trail away from the sun that gives comets their classic look. In Hubble shots, the sunward feature extended roughly tenfold its breadth. Such a stark elongation hinted at either a tightly focused stream aimed straight at the sun or a narrow dust path observed almost sideways from our planet's position. The setup is key to decoding the view. During Hubble's imaging, the Sun, Earth, and 3I/Atlas aligned so Earth sat just about 10 degrees off the Sun-comet axis. Thus, We observed nearly head-on along the solar-facing direction, maximizing the apparent length of any such feature. With a balanced haze around the object, one would anticipate observers expected to observe a somewhat rounded or oval-shaped coma, possibly with minor stretching from the development of a dust tail. However, the Hubble Space Telescope captured a striking, needle-like structure aimed straight at the Sun, accompanied by a fainter and briefer anti-solar tail extending in the opposite direction. In their study, Lowe and his colleague Eugene Quito simulated this configuration. They pointed out that the actual three-dimensional length of the sunward feature probably exceeds the 10:1 aspect ratio indicated, since our perspective slightly foreshortens it even when viewed 10 degrees away from the axis. Anti-tails aren't unheard of among solar system comets. They arise when we catch sight of a comet's dust trail in the orbital plane edge-on, causing earlier ejected particles to project ahead of the nucleus in our view, despite actually lagging behind along the trajectory. A notable case is Comet Arend-Roland in 1957, which exhibited a clear spike seemingly directed at the Sun, resulting solely from the geometry of its dust trail. What sets 3I/Atlas apart is the anti-tail's extreme proportions and luminosity compared to the anti-solar tail, implying more than mere optical illusion from projection. The Hubble study's modeling proposed anisotropic emission from a heated dayside, where dust and gas are released mainly from sun-exposed areas. This setup would produce a genuine buildup of material on the sunward face, rather than just a visual effect from our vantage point. Anisotropic outgassing frequently occurs in comets, as their nuclei aren't perfect spheres with even activity. Localized active zones, exposed volatile ice patches, or regions with varying thermal traits can direct jets in particular ways. The nucleus's spin sweeps these zones through light and dark periods, altering the outgassing rhythm. Yet, typical comets display several jets at differing orientations, not one prevailing sunward surge. Explaining why 3I/Atlas would consistently vent material directly sunward throughout weeks of monitoring calls for either a precisely configured nucleus shape and spin or a surface makeup where sun-facing sections hold distinct volatiles from elsewhere. Each option fits within natural comet behavior, though both deviate from the norm. At this point, conjectural mechanical comparisons emerge, and they must be flagged as hypothetical since we're entering a realm where science and speculation overlap. Should 3I/Atlas have a mirror-like surface instead of a dark, dusty one? Incoming sunlight on the dayside might reflect back toward the sun rather than getting absorbed and re-emitted as heat. Such mirror-like reflection could generate a focused brightening in the sunward direction, mimicking a jet in photos without any actual ejection. Imagine it akin to a solar sail, with smooth reflective sheets redirecting light based on their tilt. The comparison falters soon, as solar sails are crafted to be sleek and shiny, whereas natural objects are usually irregular and dim. Still, it highlights how material properties can produce targeted visual phenomena that could be mistaken for jets in observations. A further hypothetical idea draws on radiation pressure streams, similar to ion engine exhaust. Spacecraft ion thrusters achieve efficient thrust by speeding up ions and shooting them out forcefully. Their exhaust forms a tight, elongated plume trailing the craft. If 3I/Atlas were producing a stream of charged particles or plasma aimed sunward, maybe from solar wind interactions or an emission process, that could show up as a vivid sunward protrusion in visible light images. This notion's underlying physics remains purely theoretical, with no established natural process yielding a persistent sunward ion stream from a comet. Yet, in pondering artificial origins, targeted particle release at least seems feasible in theory. One more conceptual lens examines directed venting for temperature regulation. Designed probes handle excess heat via radiators angled to dump warmth into the void. For a structure like 3I/Atlas built to endure a solar flyby, it could use sublimation or outgassing of outer layers as deliberate cooling, favoring sunward directions to optimize heat loss. This acts like ablative shielding, with vaporizing material from the exposed side whisking away energy to safeguard the core. The involved chemistry would be crucial. Carbon dioxide sublimation, as JWSDNF carbon dioxide, established as the primary volatile, serves as an effective coolant due to its substantial latent heat of sublimation. Employing CO2 as a deliberate thermal regulation medium isn't unreasonable from a physical perspective, yet asserting that 3I Atlas utilizes engineered heat control represents a vast extrapolation beyond existing proof. Conventional accounts for the anti-solar structure have been proposed and documented. A fresh preprint on AR-14 from late September 2025 simulated 3I Atlas's sunward features through an anisotropic survival zone for evaporating ice particles. The core concept involves dust particles ejected from the core that carry internal ice, which keeps vaporizing as they traverse the surrounding haze. Particles drifting toward the sun face intensified solar radiation and evaporate faster, resulting in a group of particles that persist longer in anti-solar paths compared to sunward ones. This uneven longevity can generate a seeming buildup of finer particles or vapor toward the sun, whereas bigger particles that withstand evaporation form the typical anti-solar dust stream. The simulation mirrors 3I Atlas's documented shape without relying on manufactured components or unusual physics. It offers a straightforward natural rationale that deepens our grasp of cometary particle behavior instead of undermining the core idea that this is a comet. So, which account is more efficient? Elaborate yet believable natural asymmetric effects grounded in known physics, or basic artificial designs that demand rejecting the standard view that objects from interstellar space are innate formations? Occam's razor, favoring the least complex accounts, doesn't clearly support either side since simple hinges on your starting assumptions. If you presume interstellar visitors are invariably natural, then intricate natural frameworks remain preferable to engineered ones because they avoid the bold assertion that crafted items journey across the stars. If you're neutral on the origins of such objects, a straightforward artificial model could prove more concise than layering several rare natural phenomena. Avi Loeb proceeds from that neutral stance. Conventional astronomy assumes the natural baseline. Both viewpoints are valid, but they yield starkly contrasting reads of unclear data. What fresh data could separate artificial from natural views of the sunward form? Fluctuation trends provide a key test. If the sunward stream links to the core's spin, we'd expect rhythmic changes as active zones swing in and out of daylight. Typical natural streams display spin-driven cycles lasting hours to days, based on core dimensions and rotation speed. Should 3I Atlas's sunward traits stay constant in intensity and shape over durations exceeding likely spin cycles, that would stand out and hint at a mechanism unrelated to rotation. Detailed imagery that distinguishes the core and adjacent streams would indicate if outflows stem from specific hotspots or a broader sunlit emission. Polarization scans might differentiate dust-reflected light from mirror-like bounces off sleek exteriors. An ongoing spectral analysis of the sunward element against the antisolar tail could uncover material variances, shedding light on whether distinct particle types or processes are at play. Such measurements lack the detail and frequency needed to settle the issue for good. Hubble captured shapes but missed fine temporal shifts. JWST delivered material insights, but not sharp views of the core. Earth-based spectral work detected metallic outflows, but failed to map their precise sources spatially. The Mars close approach might have supplied vital near views from satellites, adding essential details, but as covered in the first part, that information is either uncollected, unreleased, or not yet analyzed thoroughly enough for public access. The sunward stream stays unresolved, striking in visuals and intriguing in layout, yet inconclusive on its source. This uncertainty lies at the core of why 3I Atlas has gripped the public's fascination unlike 2I/Borisov ever did. Borisov stood out chemically, with makeup unlike solar system comets, but its appearance was routinely unremarkable. It resembled a comet. It acted like one. 3I Atlas resembles an attempt at a comet that falls short. The sunward stream, the blue haze from Mars, the iron-free nickel, the path hugging the ecliptic plane. These traits merge into an overall impression that seems amiss, even if you struggle to pinpoint exactly why. And in that sensed mismatch, in the void, the difference between anticipated results and actual findings creates an opening for conjecture that would be quickly rejected if the data were more routine. We've examined the object's physical characteristics, its trajectory, its composition, and its structure. We've detailed 7 irregularities and considered whether each could stem from natural processes, artificial origins, or hybrids we haven't conceived yet. However, one key aspect of the narrative remains underexplored. It's the factor that shifts mere scientific interest towards something more ominous and rife with intrigue. That factor is the quietude, the disparity between what watchers anticipated and what official bodies supplied. The sense, accurate or not, that details are being suppressed, altered, or postponed for motives exceeding standard research prudence. This sense, along with the speculation it sparks about concealments and concealed realities, is our next focus. For if 3i/Oumuamua truly stands out, the issue extends beyond its identity. It becomes who dictates the account of its detection and the consequences when that authority falters. Part 10. Concealment right under our noses. In his essays before the flyby, Avi Loeb outlined precise hopes. The high-resolution imaging science experiment on the Mars Reconnaissance Orbiter could yield size limits at roughly 30 kilometers per pixel resolution. ESA's Mars Express and the ExoMars Trace Gas Orbiter might offer spectral analysis in infrared ranges. Perseverance's Mastcam-Z and additional tools could record nocturnal celestial views if schedulers made room. The viewing period ran from October 1st to 7th, encompassing the October 3rd nearest pass. Diverse autonomous systems, varied observation angles, broad spectral tools, all aimed at an entity monitored and forecasted for months. The scientific circle anticipated a flood of information. Instead, they received a dribble, followed by an unauthorized batch that skirted formal routes altogether. Official streams from NASA's Mars endeavors remained mute in the wake of the closest encounter. Routine updates of unprocessed photos from Perseverance persisted daily or so, depicting stones, rover paths, and Martian terrain. Nothing evident in night sky shots highlighting a dim extrasolar guest. No announcements on sightings or absences. No organized collections of refined mosaics displaying 3i/Oumuamua amid the Martian backdrop. The high-rise repository, filterable by observation codes and positional data, lacked fresh records tied to 3i/Oumuamua in the flyby timeframe, at least in the open index accessible to hobbyist analysts. Data from Mars Express stays specialized and untagged, complicating hunts for particular subjects absent internal details on scheduling. The ExoMars TGO, the most recent Mars satellite and still adapting to research routines, stuck to tracing atmospheric gases without any outward sign of pursuing interstellar sightings. This hush fits squarely into standard protocol explanations. We must acknowledge that, even as we probe why the hush resonates more intensely than indifference, interpreting data demands time, especially for unplanned diversions outside core agendas. Mars satellites and landers prioritize geology, air, weather patterns, life searching, and resource mapping for eventual crewed ventures on the red planet. Spotting a fleeting interstellar interloper is an extra, a chance alignment slotted in if resources and attitudes permit, but it yields to essential goals. Once bonus data streams in, it queues up after urgent batches. Alignment demands syncing sensor directions with exact positional forecasts for the object, requiring weights for refined tracks from ground-based monitors of 3i/Oumuamua. Validation involves scanning for device glitches, radiation strikes, and handling flaws prior to confirming presence or lack thereof. Such steps span days to weeks, rather than mere hours. Yet the delay between hope and handover nurtures space for rival interpretations. The U.S. government furlough starting September 30th, impacting certain NASA functions, served as a handy rationale. Although such pauses don't stop distance-based tasks or gathering info, outreach teams dial down. Announcements get postponed. Support staff on non-essentials take leave, which hampers the labor-heavy task of preparing releases for the public, though the craft continue functioning. Signals keep arriving at receivers. Vital evaluations proceed. The furlough hindered outreach more than performance. Yet in a tale already geared towards shadowy theories, outreach these holdups come across as intentional cover-ups, no matter the real reasons behind them. The feedback loop that boosted the Schmaus leaked Mastcam stack also spread stories about the agency's quiet stance. Blue SKX discussions overflowed with guesses on why official info wasn't surfacing. Reddit groups argued over whether Mars satellites had truly spotted the object or if the viewing schedules had been scrapped on the down low. YouTube makers churned out clips with headlines questioning if NASA was concealing signs of an alien spacecraft, pointing to the real absence of shared data as proof of a hidden agenda. Outlets like The Debrief ran pieces that tiptoed between covering public buzz and backing it, offering space for the doubts without fully buying into resolutions. With every round of hype, the gap widened from the everyday facts of standard data handling schedules, building a collective view where no word meant foul play. Past examples both ease the distrust and stoke it further. Oumuamua's find in October 2017 trailed into weeks of uncertainty around its makeup, and source. Early sightings displayed a stretched brightness pattern matching a spinning, super-stretched body. Later position measurements uncovered extra push not fitting usual comet gas ejections, since no surrounding haze appeared. Loeb's 2018 idea that Oumuamua could be an engineered light sail kicked off fierce arguments that linger on. During that stretch, info drops lagged, breakdowns clashed, and the space between first spot and expert agreement let rumors thrive. The vagueness was legit, stemming from spotting constraints and true research doubts, not from organized blocking. IM-1 echoed this path, as the space rock pickup from U.S. military detectors, unclassified and probed by Loeb's group, sparked a seabed hunt that said it snagged metal globules possibly from beyond our system. Those assertions hit quick resistance from experts who said the globules were Earth junk or wrong IDs for regular space dust balls from normal meteors. Lab tests split on atom mixes and buildups. Loeb held firm that their results pointed to crafted or odd beginnings. Detractors said the numbers lined up with everyday causes and that wild ideas rested on routine readings. The clash hangs open, yet it set a template. Loeb's open writings outpace strict reviews. Establishment experts resist reads they see as wild, and folks follow the science tussle live via blog entries and draft papers instead of holding for print journals. C/2019 Y4 Atlas slots right into this mold. Loeb's pieces pile up oddities and pose queries ahead of agency announcements. Vague sightings like the leaked Mars stack skip, check processes, and go megaviral. Agency hush, be it from care, crunch time, or ops halts, reads as proof instead of nothing. Crowd stories outpace the research ones, setting hopes that groups then scramble to fulfill, given their paces run in weeks while online buzz flies in hours. Could there be cases where groups truly hold back game-changing data? That query leans toward plots, but pondering it matters since it shapes how we read quiet. If starter picks from HiRISE or Mars Express revealed shapes totally off from a regular comet, like crisp lines or even shapes or shine hinting at built panels, would groups rush that out or first mull it inside, loop in specialists, hunt glitches in gear, and maybe sync with others before speaking? The safe bet is standout data gets heavy vetting pre-share, not from hiding urges, but since messing up cuts deep either way. Rushing an alien tag on what's just a quirky natural iceball hurts trust and sparks plot spins. Brushing off weird traits as flaws when they're not slows grasp and maybe buries huge insights. The probable truth is the dull one. Mars tools did catch C/Atlas in the pass-by slot. Certain views worked, others flopped from aim slips or bad lighting. Ongoing analysis under tight conditions. Experts handling the successful captures via standard processing workflows, balancing several initiatives amid fiscal and scheduling pressures. Early findings are being validated against theoretical frameworks, cross-referenced with terrestrial telescope data, and geared up for release via rigorous academic review. Expect this phase to span several weeks or months, far from mere days. Once findings emerge, they may well align 3I Atlas with a peculiar yet organic comet, broadening our insights into the variety of cosmic wanderers without invoking manufactured explanations. The purported Mascom Z-series leak will likely get chalked up to a data glitch, alignment issue, or at most a faint trace of hazy envelope that offers little fresh insight past JWST and Hubble's contributions. Yet this mundane outcome fails to quench the curiosity of those deeply drawn to the enigma. It overlooks why Schmaus series displayed blue hues amid prevailing green or neutral tones elsewhere. It sidesteps the cluster of 7 irregularities outlined by Lowe. It ignores the intuitive unease that grips numerous reviewers upon scrutinizing 3i Atlas's integrated dataset. Above all, it dismisses the slim yet real chance that we're encountering something contrived, that the hush reflects deliberate restraint before a reality-altering revelation, and that the escaped photo signals not a flaw but a peek at reality slipping past bureaucratic barriers. Narrative-wise, we're at a crossroads. The second act has unveiled the entity and its quirks, the exact trajectory, the odd composition, the unusual shape, and the info flows encircling it. The third act needs to grapple with consequences. Should 3i Atlas merely be an unusual comet? What lessons does it impart about the void between stars and the birth of solar systems? If it's engineered or deliberately sent, how does that reshape our view of cosmic minds and humanity's role in the grand stellar web? And for everyday folks lacking secure intel or inner circle tips, how do we bridge official statements and personal hunches? That's our path forward. For the Martian blur, authentic or glitch, has already shifted the discourse. It rendered the implausible plausible. And crossing that line means no easy retreat. Part 11. Mars, the Quiet Observer. Should the exposed series prove real? If Perseverance's Mars Cam-Z indeed snagged 3i Atlas crossing the Martian darkness, then the red planet emerges as the key corroborator for this saga. Not due to its stellar uniqueness, but because Mars provides validation routes unmatched by ground or space-based Earth views. Proximity counts, angles count, and crucially, narrative steering counts when assertions upend core beliefs about stellar travelers. Backup confirmation routes are clear to list, though pursuing them remains challenging. Martian satellites, especially the Mars Reconnaissance Orbiter with its high-rise imager, watched from spots far nearer to 3i Atlas on the October 3rd pass than any Earth telescope could. Just 29 million kilometers parted Mars from 3i Atlas at nearest point. By contrast, 150 million kilometers yawned between Earth and Mars during that orbital phase for both worlds. Factor in the evolving alignments as 3i Atlas traversed the inner system, and Martian vantage points could deliver sharper detail and luminosity detection beyond Earth's reach. If HiRISE nabbed the object clearly, records might reveal a pinpoint light, a sprawling haze, or zilch, hinging on its actual form and glow. A pinpoint would hint at a tight build. A sprawl would back the comet theory. Absence might mean it was dimmer than expected or that AIM slips block capture. Spectral scans from Martian satellites impose limits on makeup. Mars Express bears Omega, a visual and near-IR mineral mapper that theoretically could have grabbed 3i Atlas's light profile if targeted properly. ExoMars Trace Gas Orbiter's tools, tuned for air studies, suit point target spectra less well, but may have tried scans in the past timeframe. Such data would bolster JWST's makeup results, possibly spotting shifts in envelope chemistry from Mars' nearer angle. Variations in CO2 to H2O proportions by sightline, or altered strengths in metallic glow lines from Mars versus Earth could refine ideas on envelope buildup and gas release. Perseverance might have pursued follow-up scans post the first reported one. The spacecraft functions independently in the intervals between instruction uploads, though operators can prearrange series of actions well ahead of time. Should the stack from October 4th truly have spotted 3 Atlas, the team might have directed extra imaging of the night sky on following evenings to monitor the trajectory and validate the sighting. The absence of any later stacks and public viewpoints to possibilities like no orders for further checks, commands issued that didn't pan out, or positive results withheld for a unified disclosure. Each scenario holds its own consequences. Skipping follow-ups could indicate doubt in the first observation or a shift in focus to other rover priorities. Unsuccessful pursuits imply borderline signal strengths highly sensitive to weather factors and alignment accuracy. Positive results kept back for orchestrated rollout hints that involved organizations view this as a major discovery needing measured handling. Involvement from October 1st to 7th spanned various nations and entities, at minimum on paper. NASA manages the Mars Reconnaissance Orbiter and Perseverance. ESA handles Mars Express and ExoMars TGO. Protocols for exchanging data among space entities ensure that key discoveries from one program usually get shared, enabling joint viewing efforts and mutual validation. In case NASA's equipment picked up anomalies amid the 3 Atlas pass, ESA probably got notified and might have added separate data or reviews. The global nature of Martian missions implies any joint cover-up would demand collusion spanning organizations, traditions, and administrative setups that rarely mesh easily. This isn't out of the question, but it elevates the threshold for sustaining quiet across separate groups. The optics of a government closure paired with lofty assertions breed an ideal breeding ground for gossip, and that's exactly where we find ourselves. As the U.S. shutdown overlapped the Mars transit period, it offered a convenient rationale for NASA's muted outreach. Yet closures don't impact ESA's work. Mars Express and ExoMars TGO kept running as usual. Their information kept flowing into storage and processing, with European researchers encountering no closure-induced limits. If ESA's tools captured something remarkable, no closure would justify postponing news. The lack of ESA statements implies their efforts either fell short, revealed nothing odd, or remained reserved for motives akin to those behind NASA's reticence. This widespread hush proves tougher to pin on mere administrative snags, fueling ideas that hold up stem from deeper priorities beyond red tape. Mars's position offers a distinct edge over ground telescopes on Earth. 3 Atlas's path crossed Mars's leading side during the encounter, positioning the planet ideally to view the object's forward aspect, the half facing its travel direction. From Earth, angles shifted us nearer the flank or rear side based on the precise timing. Such variances count if 3 Atlas displays uneven traits in reflectivity, makeup, or form across its halves. A shiny forward surface or focused venting from the oncoming side might shine most vividly from Mars's perspective. Terrestrial watchers would catch a contrasting view, possibly dimmer or with altered color signatures. Discrepancies in luminosity or hue between orbital and planetary sightings could prove revealing, uncovering patterns and imbalances that a lone angle would miss. What might serve as decisive evidence from Mars instruments? The criteria are concise yet definitive. Steady movement across several images would validate the stack's pick as a genuine celestial target, not a glitch, since glitches lack reliable paths. Spectral signatures aligning with JWST's CO2 heavy envelope would affirm makeup uniformity and bolster the comet origin theory. Spectral features clashing with JWST, especially metallic signals at odds with comet makeup, would call for unusual interpretations. Light patterns defying a spread-out hazy envelope, such as tight cores or patterned glows, would undermine standard comet ideas. And color uniformity or variance against the blue blotch from broad filter imaging, as opposed to color process stacks, would clarify if the hue oddity is authentic or a processing error. No such clinchers have surfaced in available records. As of early October 2025, no official announcements have surfaced. This quiet void only intensifies the rumors swirling around. We find ourselves suspended in uncertainty, where the purported data leak circulates as a widely discussed phenomenon among enthusiasts, yet lacks confirmation or contradiction from fresh evidence that could clarify matters once and for all. Such vagueness can persist for several weeks, or even longer, until space agencies unveil findings from Mars missions or public focus shifts to fresh scandals. Yet for dedicated observers, those who tracked Oumuamua's enigmas and the clashes over IM-1, the recurring dynamic feels all too recognizable and aggravating. Key inquiries remain unresolved, not due to a lack of information, but because processing channels and bureaucratic restraint generate delays that conjecture eagerly exploits. Mars serves as the mute observer. Its satellites and landers likely possess details capable of clarifying arguments or amplifying enigmas. Those details linger in data feeds and storage systems, pending review and evaluation by experts. The timeline for their release, days, weeks, or months, hinges on unseen agendas and choices beyond our influence. Within that interval between occurrence and disclosure, we weave stories that might endure or crumble upon encountering the forthcoming facts. The alleged blurry image has already molded these tales, elevating 3I Atlas from an intriguing cosmic wanderer to a pivotal benchmark where proponents discern validation and doubters identify flaws. Each camp leverages Mars' reticence to bolster their stance. It's time to pause and link 3I Atlas to the overarching sequence that started with Oumuamua and extended via IM-1. If 3I Atlas merely continues the line of extraterrestrial intruders that defy our predictions, then perhaps our assumptions need recalibration, or we're glimpsing the dawn of a discovery that could redefine humanity's cosmic role. That sequence and its implications are our focus moving forward. Part 12. From Oumuamua to 3I Atlas, a pattern takes shape. 3 instances don't establish a definitive trend, but they suffice to probe whether this reflects random variation or initial signs of something more substantial. Oumuamua made its entrance in October 2017, marking the inaugural verified interstellar body spotted traversing our solar system. Its detection happened by chance, via the Pan-STARRS telescope in Hawaii, which captured it as a dim speck drifting amid the stellar backdrop. Early assessments pointed to an asteroid, a solid, barren chunk absent the gaseous and dusty envelope typical of comets. However, its path and later anomalous push deviated from the asteroid model. The detected speed-up, a departure from standard Keplerian orbit, demanded explanations like uneven venting akin to cometary activity or an alternative influence on the body. Despite thorough scans, no such envelope appeared, eliminating conventional cometary gas release. Avi Loeb, alongside colleague Shmuel Bialy, issued a 2018 study suggesting the motion could stem from Oumuamua acting as a light sail, a slender, mirroring film propelled by sunlight. The idea sparked debate, facing sharp pushback from astronomers who deemed it superfluous since faint emissions from unseen ices could account for the effect without a visible tail. Still, the concept lingered, unrefuted by later scrutiny. IM-1, or Interstellar Meteor 1, entered the narrative via an unexpected route. Sensors from the U.S. government, built for spotting nuclear blasts, logged a fireball plunging into Earth's atmosphere above the Pacific in January 2014. Years on, analysis by Loeb's group, drawing from released records, indicated an extrasolar source through its hyperbolic trajectory. The inferred durability, gauged by its fragmentation in the air, hinted at atypical makeup, possibly metallic, unlike standard rocky or frozen fragments. Loeb spearheaded a seabed search at the crash zone, collecting magnetic beads from the muck that he asserted displayed chemical signatures at odds with local solar system stuff. Rival labs challenged this, positing the beads as earthly pollutants, industrial soot from sea traffic, or routine space debris from ordinary falls. The standoff persists, with Loeb insisting his results point to engineered or at least extraordinary origins, while detractors argue the evidence has been misconstrued. 3I Atlas marks a significant leap in evidential depth over its forerunners. Oumuamua was spotted outbound, affording scant time, mere weeks, for data collection before it dimmed past reach. IM-1 unfolded in moments, yielding just entry traces and salvaged remnants as clues. In contrast, 3I Atlas was identified well ahead of its closest solar approach, enabling prolonged and thorough examination. Extended observational efforts using premier telescopes have delivered insights that earlier surveys like Oumuamua missed. JWST's spectral analysis offered definitive details on makeup that Oumuamua couldn't match. Hubble's imaging uncovered shapes invisible in Oumuamua's mere dot-like view. Earth-based spectral scans picked up metallic signals absent in both prior cases. The Mars pass-by granted proximity views unavailable for the previous intruders. 3I/Atlas stands as the most information-packed interstellar guest we've examined. Yet, precisely due to this abundance, it remains the trickiest to decipher. A collection of peculiarities sets 3I/Atlas apart from standard solar system comets far more starkly than either forerunner strayed from its peers. Oumuamua's oddity centered mainly on motion. Its non-gravitational push without an evident dust envelope marked one strangeness, while the second's quirks involved makeup, suggested material durability, and alleged isotope irregularities. 3I/Atlas merges motion-based, makeup-related, and shape anomalies into one intriguing set. The path hugging the ecliptic plane, with several planetary close calls mirrors Oumuamua's unexpected path. The reported atypical metal proportions recall IM-1's contested spheral makeup. The tail pointing toward the sun and the coma rich in carbon dioxide introduce shape and composition traits unseen in the others. Polarization data straying from established comet groups brings in light-scattering enigmas. And the possible spotting from Mars' surface, should it hold up, supplies validation from a fresh angle that reshapes the whole story. Responses from scientific bodies have shifted over these three cases as well. Oumuamua sparked early buzz, then faced core group resistance to Loeb's solar sail idea, with most experts opting for rare, yet earthly accounts tied to vapor release from substances like nitrogen or hydrogen frost. IM-1 met doubt right away, as numerous scientists challenged its interstellar status and rejected the makeup assertions from gathered spherules. 3I/Atlas has provoked a layered response, featuring solid core science studies portraying it as a quirky yet ordinary carbon dioxide-laden comet, alongside Loeb's side story, casting it as maybe engineered or at least warranting deep probe into that possibility. Releases from NASA and ESA stress the comet angle, spotlighting JWST's makeup revelations and accounting for the sun-facing features via standard vapor models. Press reports divide, with some stressing the standard comet tail and others boosting Loeb's outlier perspective. The Guardian ran a piece in late September directly countering extraterrestrial gadget views, citing experts who said 3I/Atlas's traits are atypical but fit within comets' natural variety. The story pointed out that carbon dioxide-heavy comets occur in our system, that sunward tail setups have rational causes, and that pinning odd traits on man-made routes demands much firmer proof than we have now. Such firming up from trusted news sources plays a key role in the info landscape. It counters wild guesses by anchoring public views in specialist agreement, even if that agreement lacks the thrill of rival takes. The Galileo Project, Loeb's effort aimed at methodical hunts for tech traces from alien societies, runs on a principle of open-minded yet evidence-driven inquiry. Its slogan admits big assertions need backing, but insists prejudging tech ideas without data review is anti-science. This approach casts Loeb and his team as data-following doubters, not devotees, ready to chase clues no matter the direction instead of forcing fits to safe ideas. Detractors claim this stance is one-sided, that Loeb spotlights tech angles while minimizing everyday options, fostering a sense that the findings back artificiality when they truly don't. The clash revolves around research methods and outreach as much as raw sightings. The trend spanning Oumuamua, IM-1, and 3I/Atlas shows growing layers of puzzle and detail. Each new interstellar arrival has yielded richer datasets, better chances for in-depth study, and traits that defy easy labels. Should this hold, upcoming interstellar finds will get spotted sooner, tracked more thoroughly, and produce even denser info troves that could clear up uncertainties or amplify them. Whether this path points to agreement that interstellar bodies vary naturally in unforeseen ways or builds toward proof that certain ones, whether a significant portion of interstellar travelers consists of manufactured remnants, is still an open question. However, 3I/Atlas, blending thorough data collection with ongoing peculiarities, stands as the most rigorous challenge so far in distinguishing between organic and engineered origins. It's essential to outline the possibilities clearly. So, what rival theories account for 3I/Atlas, and what evidence would settle the debate? That forms the conceptual groundwork for the upcoming part, after which we'll explore why this instance seems distinctly apart from past disputes, and what that distinction reveals about our preparedness to address ideas we've long overlooked. Part 13. Conceptual models. 3 rival paradigms seek to encompass all the data gathered on 3I/Atlas, with each one bearing consequences that extend well past a lone celestial body. We'll scrutinize them thoughtfully, as they merit. Selecting among these models isn't merely an intellectual pursuit. It reflects our views on the universe's potential and our approach to inconclusive findings. Model A positions 3I/Atlas as an immense comet of natural origin, an unusual, yet essentially conventional entity shaped by mechanisms we grasp, even if their precise results are unfamiliar. The abundance of carbon dioxide, solidly confirmed via JWST's near-infrared spectral analysis, aligns seamlessly with this view. JWST detected CO2 to H2O proportions of about 8:1, exceeding those in ordinary solar system comets. Yet this can be attributed to formation beyond the carbon dioxide frost boundary in its home star system. That frost line lies further out than the water one, demanding even lower temperatures for CO2 to solidify. Bodies emerging in such frigid outer zones would gather CO2-laden ices, while water ice might have evaporated from prior warmth or been scarce at that range from the star. Spherex's survey of the expansive CO2 envelope, stretching over 348,000 kilometers, verifies intense, ongoing degassing from a sizable, ice-heavy core reacting to sunlight as it nears its closest solar approach. The Hubble Space Telescope's depiction of the sun-facing anti-tail, attributed to uneven venting from a warm daytime side, slots easily into this model. Irregularly shaped comets with patchy surfaces often display jets and uneven forms. While 3I Atlas's sunward protrusion tests the boundaries of norms, it doesn't shatter them. A fresh preprint simulation of the anti-tail via varying sublimation speeds in icy dust particles offers a grounded explanation that matches the scene structure without resorting to rare phenomena. Dust particles oriented toward the sun would vaporize more quickly, mimicking a buildup in that area despite a potentially balanced overall release. This involves nuanced dynamics, yet it fits squarely within standard comet activity. The polarization data, though odd in excluding 3I Atlas from established comet categories, can still match natural particle sets if we consider atypical sizes, forms, or makeups. Such readings hinge closely on particle traits. Given just a handful of thoroughly studied comets as benchmarks, the range of natural dust variations is undoubtedly broader than documented. 3I Atlas could merely reveal a novel dust type, broadening our knowledge of comet particles rather than signaling something constructed. The metallic signals, nickel and iron atoms in the envelope, remain intriguing due to their proportions and heat demands, but similar detections now appear in other comets. Explanations are still under discussion, though organic metal bonds and sun-heated metal-infused grains offer credible natural routes. Model A's advantages lie in its restraint and grounding in proven principles. It demands no novel core theories, no rejection of the idea that interstellar objects are organic, and no call to alien intellect or design. Its drawbacks are just as apparent. It demands piling several rare traits, each edging natural norms into one entity. Elevated CO2 levels, drastic anti-tail shape, odd metal balances, quirky polarization, and a near-plane orbit, all defensible singly, but jointly unlikely. At what point does layering improbable traits make broadening natural variety less efficient than exploring other options? That's subjective, not quantitative, and experts with varying backgrounds will set that threshold differently. Model B proposes a broken-apart interstellar craft, admittedly conjectural, yet deserving review based on its engineering viability. This approach BR interpretations of the nickel-enriched outgassing suggest engineered substances vaporizing due to solar warmth, featuring nickel-to-iron proportions that indicate intentional alloy selections instead of typical cosmic distributions. Manufacturing processes for stainless steels and advanced alloys incorporate nickel levels well beyond those found in nature, as it boosts resistance to rust, tolerance for extreme heat, and various beneficial traits. Should 3I/Atlas represent a spacecraft or remnant built from these substances and currently under thermal strain near perihelion, the eroding exterior would expel metallic particles with these crafted compositions into the void. Such particles would show up in spectra as unusual signals. This aligns precisely with what Lowe describes observing in 3I/Atlas's spectral data. Under this perspective, the sunward anti-tail emerges as a byproduct of heat regulation or an effect from radiation pressure. If the entity boasts a highly reflective outer layer tuned to reduce heat intake, reflected sunlight from that layer might produce a luminosity boost toward the sun, potentially mimicking a gaseous outburst in telescopic views. On the other hand, if the craft is intentionally directing heat dissipation via targeted erosion, favoring material loss toward the sun to optimize cooling. That could generate an authentic outflow pattern consistent with the sightings. The CO2 laden coma might function as a purpose-built refrigerant, chosen for its substantial sublimation energy and non-reactive nature. Alternatively, it could act as a cover, with a layer of easily vaporized ices applied to lend the appearance of a standard comet from afar, hiding any organized core beneath. In this setup, the trajectory hugging the ecliptic plane with its series of planetary flybys stands out as a core characteristic, not mere chance. A probe crafted to examine our solar system would logically opt for a path skimming the planetary plane, enhancing data collection through successive near misses with several planets in one journey. The schedule, packing in Venus, Earth, Mars, and Jupiter passes over just 6 months, points to clever planning rather than fortunate alignment. The estimated dimensions, possibly reaching 5 kilometers or more from luminosity and motion limits, fit an expedition spanning stars, where protection, propellant, sensors, and backups require substantial bulk and capacity. Though tinier craft could save on fuel, bigger versions offer greater durability against tiny impacts and cosmic rays during voyages lasting thousands or millions of years across the interstellar gulf. Compelling proof for this artificial scenario would involve light variations with clear organization, defying erratic spins, or recurring signatures hinting at deliberate attitude control over haphazard spinning. Detailed images uncovering shapes, boundaries, facets, or uniform patterns would clinch the case. Spotting spectral lines in emissions or absorptions lacking any natural basis, along with lab-made compounds or isotope mixes unachievable via stellar fusion or ordinary reactions, would demand reckoning with a manufactured source. Broadcast radio waves or pattern light pulses would serve as undeniable indicators. So far, none of these signs have appeared, leaving the idea reliant on readings of unclear observations instead of straightforward confirmations. The third scenario delves into a fabricated comet facade. This highly conjectural view posits that 3I/Atlas is inherently constructed, yet engineered to imitate a genuine celestial wanderer up close. Glossy finishes or sleek shells might get cloaked in a sheath of sublimating frosts, dry ice, water, and such, that activate in sunlight, yielding the look of typical cometary behavior. The azure haze spotted from Mars' vantage could reveal the inner shiny framework where the frost cover thins out or vanishes, exposing a neutral or bluish reflection distinct from the reddish dust glow prevalent elsewhere. The CO2 veil plays double duty, aiding in heat control via vaporization and providing visual deception through spectral traits that experts would chalk up to cometary origins. Testing this idea proves challenging, as it's built for ambiguity. An effective masquerade, inherently, replicates natural traits closely enough to sidestep suspicions of artifice without meticulous scrutiny of minor discrepancies. Yet the logic falters in key ways. What purpose would camouflage serve for an interstellar visitor? For true secrecy, skipping our system entirely would outperform any entry ploy. For open contact, bold transmissions would outpace faint oddities that spark arguments over agreement. Camouflage only fits if the aim involves targeted disclosure, striking enough to draw eyes from sophisticated watchers, yet vague sufficient for deniability or to prevent widespread alarm among more primitive societies might view such advanced setups as otherworldly. This form of strategic analysis regarding extraterrestrial motives remains purely conjectural, yet it defines the conceptual realm for Scenario C. Overlapping empirical forecasts enable us to monitor data points that could differentiate between these possibilities. Precise measurements of nickel versus iron abundances, obtained via high-fidelity spectral analysis at various solar distances and viewing angles, could reveal if the metallic signatures stay uniform, bolstering the case for deliberate construction, or fluctuate, aligning with organic irregular vapor release. Tracking shifts in polarization data as 3I/Atlas recedes from its closest solar approach would indicate whether particle traits evolve with proximity in patterns matching typical evaporation or persist in oddly steady fashion. Observations from elevated platforms, or the James Webb Space Telescope might limit the core's dimensions and shape, separating dense, shiny bodies from spread-out hazy ones. Reprocessed Martian imagery stacks, conducted openly with external checks, could settle if the azure blur is genuine or merely a glitch. Avi Loeb's progression through his online articles has shifted from portraying 3i/Atlas as peculiar to employing phrasing that hints at manufactured origins, all without outright assertions. This nuanced approach upholds scholarly integrity by steering clear of bold declarations, while subtly encouraging readers to entertain ideas they might typically reject. The tactic succeeds in drawing much broader public interest to 3i/Atlas than to 2i/Borisov, even though both qualify as extrasolar visitors. If it advances knowledge or merely dramatizes uncertainties hinges on one's viewpoint. Detractors claim it clouds rational discourse by treating guesses on par with proven results. Advocates contend it fosters openness to options that rigid academia could overlook too soon. These hypotheses expose a core dilemma in proof and analysis. To what degree of vagueness do we allow before exploring unconventional theories? How many oddities must accumulate before ordinary variation seems less straightforward than intentional crafting? No neutral resolution exists, as it hinges on baseline beliefs about the prevalence of crafted versus organic items beyond our system. Should you assume advanced societies abound and a portion pursue deep space ventures, then engineered accounts for bizarre entities warrant close scrutiny once routine interpretations demand too many flukes. If you posit advanced societies are scarce or cosmic journeys too daunting, then everyday accounts stay favored, even if they pile on improbable traits, since crafted ones appear even less plausible by default. 3i/Atlas fails to ease this clash. Instead, it intensifies it. By doing so, the entity sparks dialogue on our institution's preparedness, whether our research and societal frameworks can cope with revelations that upend basic notions of isolation in the universe. Part 14. The Haze That Alters Perceptions. Duration, 0.5 seconds. Revisit the picture once again. A subtle azure patch amid the dark Martian sky, compiled from several Mastcam-Z exposures posted on Blue Sky. Boosted via Medium, contested on platforms, yet never validated or debunked by the organizations holding the unprocessed files that could clarify its nature. Be it a data error, a misread, gaseous envelope, or a peek at crafted tech, this haze symbolizes all the oddities surrounding 3i/Atlas. It serves as the eye-catching element drawing in those uninterested in spectral details or trajectory calculations. It sparks perpetual discussion through its unresolved status, with no verification or dismissal to end the inquiry. And as an unauthorized release, it shattered the official grip on the tale, illustrating how in an age of open datasets and adept amateur analysts, control over facts is leaky and unreliable. Competing realities overlap, demanding we embrace them together. The firm evidence stands solid and noteworthy. The JWST's near-infrared instrument produced detailed spectra revealing dominant carbon dioxide, with a CO2 to H2O proportion of 8 plus or minus 1. A sturdy makeup result that withstands thorough error scrutiny. SOFIA outlined a broad CO2 halo extending hundreds of thousands of kilometers, verifying strong ongoing gas emission from a sizable, ice-laden core. The Hubble Space Telescope imaged the form, displaying a forward-pointing stub with faint backward extension. Peculiar layout that simulations link to uneven daytime venting. Earthly spectral surveys spotted neutral nickel and iron lines, broadening the catalog of metallic comets and prompting inquiries into release processes. Polarimetric observations positioned 2i/Borisov beyond the established boundaries of comet characteristics, although these findings remain compatible with broadened simulations of dust particles. Such datasets originate from premier observatories, analyzed by specialized groups, and detailed in preliminary reports and publications. They offer substantial insights into the variety of interstellar bodies, irrespective of our final conclusions about their significance. Moreover, the notion of a data breach strikes a chord as a socio-cultural and communicative event. The sequence of events, discrepancies in hues, periods of quiet, visual cues from outages, oversight of international datasets, All these factors converge to spark intense conjecture. This cannot be brushed off merely as unfounded theorizing. The uncertainties exist, even if the resolutions prove ordinary. The vagueness is authentic, even when conventional explanations hold true. The demand from the public for swift updates clashes with the methodical processes of organizations built for rigorous validation. In this tension, unofficial releases and amateur analyses step in to address the spaces left by formal outlets. Grasping this interplay is equally vital as decoding the entity itself, since it influences the acceptance and debate surrounding upcoming revelations. For those eager to track this narrative with care, the path forward is simple to outline, though tough to pursue. Targeted upcoming observations could clearly favor organic or engineered origins, and we ought to await those results instead of allowing guesses to dominate. Detailed imaging of the core via advanced telescopes like JWST or devices that can discern 2I/Borisov at fine resolutions would separate point-like emitters from diffuse structures. Persistent odd nickel-to-iron signatures over various solar distances and viewing setups would bolster arguments for irregular makeup. Polarization data spanning broader phase angles could verify if particle traits are genuinely aberrant or merely atypical in the surveyed domain. Confirmed detections of the blue patch on Mars imagery, with open methods and third-party checks, would clarify if it's a true feature or an error in handling. Ongoing spectral scans of changing spectral lines would indicate if gas release is steady, rhythmic, or displays irregularities defying standard spin and warming. Yet, none of these probes are assured. Access to scopes is fiercely contested. Planners for Mars probes prioritize core goals unlinked to fleeting cosmic intruders. Fiscal limits curb the scope of pursued initiatives. 2I/Borisov dims as it recedes post-closest approach, complicating later views. The chance for conclusive data might vanish prior to resolution, rendering 2I/Borisov as enduringly puzzling as Oumuamua, a compelling example that avoids endorsing or debunking unusual ideas, yet highlights our lingering gaps in knowledge about the space between stars and its wanderers. The haze might not conceal the essence. It could obscure what we lack the readiness to confront. This scenario caps our exploration. Suppose briefly that 2I/Borisov is engineered, that the odd LOE dataset stacks signals intent rather than chance, that the metal proportions, solar-facing shape, and near-plane path suggest design over rare origins. What would that imply for humanity as a whole, facing proof that technological ventures into the void are not ours alone? The repercussions ripple across tangible and profound realms. Tangible, as it would affirm ventures like the Galileo Initiative and redirect funds to methodical hunts for artificial markers. Profound, as it would dismantle the premise of universal isolation, compelling a re-evaluation of our role in an abruptly denser, more intricate cosmos. Yet consider the reverse. Envision 2I/Borisov as precisely what consensus astronomy deems it, an unusual yet organic icy body from outside our system, born under unseen circumstances but fully accountable via established principles. The outcomes remain deep. It would show that the interstellar realm yields far greater object variation than our local neighborhood reveals. That icy wanderers abundant in carbon dioxide, with peculiar metal glows and odd light scattering, arise and drift nearby from time to time. And that our models for icy body origins and development require widening to encompass this wider spectrum. We would gain key lessons about our own ways of knowing, too. That unclear evidence sparks heated discussions where assumptions and lenses weigh as heavily as the evidence. That formal research and lay interest run on mismatched timelines and motivations. And that upholding suitable balancing doubt with a willingness to embrace unexpected revelations is tougher than it might seem. Each possibility imparts a key lesson. Each advances our comprehension, despite heading in contrasting ways. The most unfortunate scenario involves lingering uncertainty, where the 3I/Atlas signal vanishes from sight prior to conclusive data settling the fundamental issues, resulting in a treasure trove of information that backs several conflicting explanations without an obvious route to select among them. That's the current position of Oumuamua. It continues to spark arguments long after departing the inner solar system. It's still cited in discussions of both organic and engineered theories. Proponents keep bolstering their arguments. 3I/Atlas faces a similar destiny unless subsequent sightings emerge promptly to make a difference. The imperative is straightforward. Keep an eye on critical data drops that count. Observe if stringent limits show up in Mars Reconnaissance Orbiter records. Scan for JWST or ESO outputs. Track follow-up findings in preprints or announcements. Seek out separate reviews of the Mastcam-Z images if NASA releases them openly with enough details for replication. Monitor if nickel-to-ion proportions hold steady or shift with new spectral data. Follow refinements in polarization data through extra observations. These elements are what will tip the scales, either clarifying the puzzle or intensifying it. And as you await these insights, hold on to a fitting sense of intellectual modesty. We're not certain what 3I/Atlas truly is. We possess readings, simulations, and analyses, yet the readings are limited in scope and accuracy. The simulations rely on premises, and the analyses draw on biases that vary by expert. The azure blur spotted from Mars, whether genuine or not, has already transformed the dialogue by rendering the improbable plausible. It's alerted countless individuals to the reality of interstellar wanderers traversing our solar system, to our ability to study them using ever more advanced tools, and to the potential for findings that upend our cozy beliefs. That evolution in collective awareness carries worth, regardless of whether 3I/Atlas turns out to be just another ordinary comet. It equips us for an era when spotting interstellar arrivals grows commonplace, when puzzling instances like this multiply, and when we'll require robust approaches to evidence and reasoning that many of us lack at present. Perhaps the blur is merely revealing what's actually present, a subtle trace of a carbon dioxide envelope viewed from Mars' distinctive angle amid a near pass. Tinted blue via image processing decisions unrelated to actual properties. Perhaps it's disclosing voids, an error from image stacking techniques, or a device anomaly that coincidentally lands at the spot we anticipated something. Or perhaps, against all odds, it's validating what Loeb has proposed from the start. A peek at sunlight bouncing off an exterior not crafted through buildup in a young star system's disk, but molded deliberately in a manufacturing site circling a far-off sun, dispatched our way eons or ages past, and only now divulging subtle clues of its authentic essence to those perceptive or fortunate enough to spot the anomalies. We can't say which. No one can, for the moment. Possibly never. Should the additional data fail to appear or fail to dispel confusion, one truth remains clear. 3I/Atlas serves as a benchmark for managing findings that straddle the boundary of natural and constructed, of reassuring and disquieting, of anticipated discoveries and genuine surprises. Our approach to that territory, as researchers, reporters, and informed observers, will influence not only our grasp of this specific entity, but our preparedness for future encounters. After all, no matter if 3I/Atlas emerges as the third ordinary interstellar comet or the inaugural verified engineered interstellar craft, it won't mark the final oddity we spot drifting through our stellar locale. The cosmos stretches wide. The Milky Way has endured for billions of years, and our diligent scrutiny of interstellar travelers is barely underway. The successor to Oumuamua, or 3I/Atlas, might surface tomorrow, in a year's time, or a decade hence. When that happens, we'll handle it more adeptly if this episode has taught us to harmonize disbelief with receptivity, prudence with inquisitiveness, and established knowledge with crowdsourced checks. The blur, come what may, has presented that chance. Seizing it rests with us.